Quick note before we start. This is a single combined video containing every lesson from my arithmetic playlist. I may occasionally add, update, or fix a video. Check the playlist for the latest version. Thanks for watching. Now let's get to the video. Welcome to the Arithmetic Course. Arithmetic forms the foundation of mathematics. First of all, no mathematical prerequisites are required to take this course. Why learn arithmetic? Here are 3 good reasons. It provides practical skills that can be useful in everyday life. Because arithmetic is the foundation of mathematics, it's necessary for studying more advanced subjects. It develops critical thinking and problem-solving skills. What are the real-world applications of arithmetic? Finance and marketing. Arithmetic is essential for budgeting, financial planning, and setting goals. Science and engineering. Mathematics is the language of the sciences. Chemistry, physics, biology, and engineering all rely on numeric ideas. Education. Arithmetic is the bedrock of all further math learning. Everyday life. Arithmetic helps with everyday tasks, shopping, measuring, scheduling, and more. This is an overview of the topics we will cover in the course. The first section is that of numbers, where we will give an introduction to arithmetic, numbers, operations on them, and much more. Next, fractions. What they are, how to operate with them, how to simplify, and practical uses. Then, decimals. What they are, and how to perform arithmetic with decimal numbers. We cover percentages, ratios, and proportions, conversions, and practical problems. A section on units of measurement and conversions, metric and imperial systems, the international systems of units, SI, temperature conversions, and more. Finally, we will look at other useful concepts, special cases in arithmetic, and a few foundational mathematical ideas. Arithmetic. From Latin arithmetica, ars, from Greek arithmetike techne, art of numbering. What is arithmetic? Arithmetic is the branch of mathematics that deals with the study of numbers and the basic operations performed on them, such as addition, subtraction, multiplication, and division. Arithmetic serves as the foundation for higher-level mathematical concepts and is essential for understanding and solving a wide range of real-world problems. Numbers. What are numbers? Numbers are symbols used to represent quantities and values. These are the numbers, in that order, from 0 to 9. 0. The symbol for 0 is the one in red, and below it is the number in words. Down, you see the quantity that symbol, the number 0, represents. The number 0 does not represent any quantity, and therefore have not shown anything. 1. The number 1 represents a single quantity, a single element that I've represented here through an apple. So the number 1 corresponds to a single object. 2. Here we have added an apple. The number 2 represents two elements, two apples in this case. 3. 4. 5. 6. 7. 8. 9. These are the numbers from 0 to 9. This system of numbers is called the decimal number system, or the base 10 positional numeral system, because it uses 10 digits from 0 to 9. And its origin derives from the number of fingers in our hands, 10, 5 per hand. Brief history of numbers. The Sumerians. They developed one of the first number systems, which was a base 60 system. This system was used for accounting, astronomy, and resource management. Their cuneiform writing on clay tablets allowed us to understand their numerical techniques. The legacy of the Sumerian system is still visible today in the 60 seconds of a minute, the 60 minutes of an hour, and the 360 degrees of a circle. The ancient Egyptians. The Egyptians used hieroglyphic symbols to represent numbers. For example, the symbol for 1 resembles a simple line, the one you see here, while 10 was represented by a drawing of a yoke for cattle, this one here. So here you can see a few of the hieroglyphs used by the ancient Egyptians. The Babylonians. The Babylonians recorded mathematical calculations on clay tablets using cuneiform writing. Their base 60 number system included wedge-shaped symbols for numbers. You can see them here from 1 to 59. 60 digits in total. Ancient Greeks. They developed geometric concepts and used letters from the Greek alphabet as numbers. The one you see here, so for example, The letter alpha corresponds to the number 1, for beta 2, for gamma 3, and so on. Greek mathematicians such as Euclid and Pythagoras created seminal works that still influence geometry today. In addition, they introduced theorems and postulates that form the basis of Euclidean geometry. The Pythagorean theorem is one of the most famous results of this period, fundamental for the geometry of triangles. Ancient Romans. They used Roman numerals, a system based on letters such as I, V, X, L, C, D, and M. There are these that you can see here. So the letter I indicates the number 1, double I is 2, this is 3, IV is 4, V is 5. The letter V preceded by an I means 5 minus 1, which is 4. While the letter V succeeded by an I means 5 plus 1, which is 6. So VI is 6. This is 7, this is 8, IX is 9, X is 10. So the letter X preceded by an I is 10 minus 1, which is 9. X is 10 as we said, L is 50, C is 100, D is 500, and M is 1000. This system was used throughout the Roman Empire for numbering and accounting. Despite its complexity, it remains in use to indicate years, book chapters, and clocks. Arabic numerals. There are these that you can see here. From this, there are the numbers we use today. They spread the Indo-Arabic numeral system in the Islamic and European world through translations and scholarly works. Arab mathematicians such as Al-Khwarizmi were instrumental in this process, writing text that made a number system accessible to a wider audience. Modern notation. The development of symbolic notation in the 17th and 18th centuries, particularly by mathematicians such as René Descartes, Gottfried Wilhelm Leibniz, and Isaac Newton, paved the way for calculus and modern algebra. Newton's contributions to calculus, along with those of Leibniz, laid the foundation for much of modern mathematical analysis. So these are the three scientists. In the center we have Sir Isaac Newton, on the left we have Leibniz, and on the right Descartes. Numerical systems. There are several numerical systems, and while we focus on base 10, others are widely used. Base 2, or binary, has only 2 digits, 0 and 1. This system is primarily used in computers. Base 8, or octal, has 8 digits, from 0 to 7, also useful in computing. Base 10, or decimal, ranges from 0 to 9 and likely originates from counting on our fingers. Base 16, or hexadecimal, is also used in computers, using digits 0 to 9, with letters A to F representing values from 10 to 15. Finally, there is base 60, or sexagesimal, used by the Sumerians and Babylonians, covering numbers from 0 to 59. The hands illustrate a counting technique for 60, where one hand counts the 3 finger segments, phalanges, while the other hand tracks the counts of the first. These here are the 3 phalanges of a finger, the 3 bone segments of the finger. So with 4 fingers here we have 12 segments. So in this hand we keep track of the finger segments, while on this hand we keep track of the repetition of the first hand. So if we have 4 fingers here, we count 12. And if we have one finger here, one finger up, we count 12 times 1. So 1 repetition, so it's 12. If we have 2 fingers, is 2 repetitions, so 12 times 2, which is 24, and so on until 60. Numbers up to 100. From 0 to 9. After 9, if we add another unit, a 1, we have to go back to 0, but this time with a 1 in front of it, because the numbers only go from 0 to 9, and we don't have any other symbols. So we get 10. Then, if we increment by 1 again, we do the same step, going from 0 to 1, getting 11. And so on, up to 19. After 19, adding one more, we start again, but this time with a 2 in front of the 0, getting 20. As 20 to 29, 30 to 39, 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89, 90 to 99. When we reach 99, adding a unit no longer gives us space in 2 digits, and we go to 3 digits, getting 100. From 100 to 1000. After 100, we have a series of numbers between 100 and 200, such as 101, 102, and so on, until we get to 199. If we add 1 to 199, we get 200. The same goes for the other hundreds. Between 200 and 300, we have all the numbers up to 299, and so on. In the end, we arrive at 1000. So here after 300, we have 400, 500, 600, 700, 800, 900, and finally 1000. I wrote the number 1000 with a space for clarity, but it can be written either with or without the space between 1 and the zeros. By the way, the word 100 and even 1000 is never plural, so you don't have to add a s. It's always singular. The abacus shown here is an ancient tool used for basic mathematical calculations, such as addition and subtraction. It consists of rows of colored bits that can slide back and forth on rows. Each row typically represents a decimal place, like units, tens, hundreds, and so on. By moving the bits, numbers can be visually represented and calculations made in a practical, hands-on way. So for example, the first row is for the units, the second for the tens, and the third for the hundreds. And moving the bits, you can represent numbers and make calculations. From 1000 to 1 trillion. After 1000, if we add a 0, we get 10,000. And there are many numbers in between 1000 and 10,000, up to 9,999, and adding a 1, we get 10,000. After 10,000, if we add a 0, we get 100,000. If we add one more 0, we get a million. A million is a 1 followed by 6 zeros. Then we have 10 million, 100 million, 1 billion. 1 billion is a 1 followed by 9 zeros. Then if we add one more 0, we get 10 billion, 100 billion, and finally 1 trillion. 1 trillion is a 1 followed by 12 zeros. Between each major figure, there are many added numbers, and over a trillion are still infinite numbers. But for now, we stop at a trillion, which should be sufficient for most calculations. To make it easier to read, note that each third digit, starting from the right, has a space for clarity, as in 1 million. So as we said before, I kept a space between the zeros to make it clear, but you can also keep the the one with the zeros close together. Furthermore, it is also possible to denote this through the use of a comma. The number line. A number line is a horizontal straight line that represents numbers at regular intervals, with positive numbers to the right of the zero and negative numbers to the left. It is used to show the position and order of numbers. The one you see here, from 0 to 10 and beyond, is the number line. To the right of the 0, there are positive numbers, and to the left of the 0, there are negative numbers. Basic operations. There are 4 basic operations. Addition, which uses this plus symbol. Subtraction, with a minus symbol. Multiplication, with a symbol that resembles an X, but we can also use a dot. Division, with this sign here, but we can also use a slash. Addition. Addition is a mathematical operation that allows you to combine 2 or more numbers to find their total sum. For example, here we have 3 apples, and if we buy 2 more, if we add 2 more apples, we get 5 apples in total. The members of the addition are called addends, and the result is called the sum. On the number line, we start from the number 3, and we move right up 2 steps, and we get to 5. The 3 is the apple that we add, and we move 2 to the right because we added 2 apples, and we get to 5. Here we add the numbers 58 and 34 together. We place them in this way, the tens under the tens, so 5 and 3, and the units under the units, so 8 and 4, and then we put the plus sign here on the left of 34, and we put a line below it. Then we start the addition with the units, so we do 8 plus 4, which is 12, which cannot fit in the column of units, so we write the 2, which is a unit, but we bring the 1 in the columns of the tens, because it's a tens. We do 5 plus 3, which is 8, and then we add this 1, which is the carried one from the previous addition, between 8 and 4. So 5 plus 3 it's 8, plus 1 it's 9. So 58 plus 34 is 92. Subtraction. Subtraction is a mathematical operation that determines the difference between numbers by removing the value of one number from another. In this example, we have 5 cookies, and if we eat 2 of them, we are left with 3 cookies. In a subtraction, the first number of the operation is called the minuend, which is the 5 here. And the number that is subtracted from the minuend is called subtrahend, which is the 2 in this case. The result of this operation is called difference. In the number line, we start from the number 5 and we move 2 steps left and we get 3. Now we do 58 minus 34. Like before, we place the units below the units in the column of the units, and we place the tens below the tens, so 5 and 3. Then we do 8 minus 4, which is 4. And then we do 5 minus 3, which is 2. So 58 minus 34 is 24. Here we have another example. We do 23 minus 18. When we have to calculate 3 minus 8, we see that it is not possible because 3 is more than 8. So we borrow a tens from the 2 and the 3 becomes 13. We draw a slash through the 2 to indicate that we have borrowed a 1 from the tens column. We write this 1 for the 3, which becomes 13. And we write a 1 because the 2 becomes a 1. Because we borrow a 1 to the 3. So then we do 13 minus 8, which is 5. And then we do 1 minus 1. We don't subtract 2 minus 1 anymore because we already borrow 1 from the 2. That makes the 2 become 1. So we subtract 1 minus 1, which equals 0. So 23 minus 18 is 5. Multiplication. Multiplication is a mathematical operation that calculates the total of a number added to itself multiple times. So here we have 4 bags with 3 apples in each bag, and we want to know the total number of apples. So we count them. So we do 3 plus 3 plus 3 plus 3, which is equals to 12. This repetition of the number 3 can also be written as 3 times 4 in this way, with the 4 indicating the number of times that the 3 must be added to itself. So in this way, with this operation, we are essentially saying that we have to add 3 to itself 4 times. So it's like doing 3 plus 3 plus 3 plus 3, which is 12. The first member of multiplication is called multiplicand, and the second is the multiplier, and the result of this operation is the product. In addition to the multiplication symbol, we can also use the dot, this one here, to indicate a multiplication. In the number line, we start from the number 0 and repeat the number 3 4 times. So we do 0 plus 3, which is 3, plus 3, plus 3, plus 3, getting to 12. Let's take the number 12 and multiply it by 7. So first of all, we do 7 times 2, which is 14. So we write the 4 and we carry the 1 in the tens columns. Then we do 7 times 1, which is 7. And this one that we carry, we add it to the result. So 7 times 1 is 7. Plus this one, we get 8. So 12 times 7 is 84. Let's calculate 58 times 34 by separating the calculation. First, we do 4 times 58. Then we move on to 3 times 58. So first of all, we do 4 times 8, which is 32. We write 2 and we carry the 3. Then we do 4 times 5, which is 20, plus 3 is 23. We write the 3 and we carry the 2 in the hundreds. And now we write it. Then we do 3 times 58. Here the 3 represents 30 because we're working with tens. To indicate this, we write a 0 in the units column. Then we do 3 times 8, which is 24. We write the 4 and we carry the 2. Then we do 3 times 5, which is 15, plus 2 is 17. We write the 7, carry the 1, and then bring it down. So we get 232 and 1740. So now we sum these two, and we get 1972, because we had done 2 plus 0 is 2, 3 plus 4 is 7, 2 plus 7 is 9, and 1. So 58 times 34 is 1972. Multiplication tables. Times tables are lists of products obtained by multiplying a fixed number by the numbers from 1 to 10. For example, the multiplication table of 2 is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. You can see the multiplication table of 2 here. We have 2 times 0, which is 0. 2 times 1 is 2, up until 2 times 10, which is 20. Next to it, we have the multiplication table of 3, which start from 3 times 0, which is 0, and up until 3 times 10, which is 30. Finally, we see a 10 by 10 grid that contains all the multiplications for the numbers from 0 to 10. To use it, we choose a number from the column and one from the row, follow the lines to where they meet, and find the result. So for example, we pick 2 from the column, and we pick 4 from the rows, and we follow the lines, we follow where they meet, which is 8. So 2 times 4 is 8, or 4 times 2 is 8. Division. Division is a mathematical operation that determines how many times one number is contained in another. So, for example, if we have 12 cookies and we want to divide them equally among 4 friends, we have to subtract 12 minus 4 3 times to get to 0. In this way, we find how many cookies each friend receives. So, if multiplication is the repetition of addition, division can be thought as the repetition of subtraction. So here we have the 12 cookies, and here we have our 4 friends. And if we do this operation, we get that each friend will receive 3 cookies. Other than the division symbol, we can also use the slash to indicate division. In the number line, we start from the number 12, and we remove 4 cookies at a time until we reach 0. We then take 3 steps of length 4 along the number line, starting at 12 and stopping at 0. Each step represents a portion for a friend. In the end, we get 12 divided by 4 is equal to 3, which is the number of cookies per friend. Let's take the operation 60 divided by 12 equals 5. We represent it graphically in this way, and we put the dividend, the number 60, at the bottom below the line. We write the divisor, the 12, next to it on its left. Then the quotient, the result, on top of the line, the 5. If we had a remainder, we would write it under the dividend. In this case, however, there is no remainder. Now we calculate 84 divided by 7. So we write them. Now we take into consideration the first number that is higher than 7, which is 8. And we check how many times the 7 is contained in the 8. So we do 7 times 1 is 7. 7 times 2 is 14, which is too big. The 14 is too big, and therefore the 7 is enough for us. Then we take how many times the 7 is contained in the 8, which is 1, and we write it in the result. And then we take the 7, and we write it below the 8, and we do a subtraction. 8 minus 7 is 1, which is the remainder. 8 divided by 7 is 1, with a remainder of 1. Then we look how many times the 7 can be contained in 1. The 7 is too big to fit in the 1, so we also bring down the 4. And now we consider 14. And we check how many times 7 goes into 14. So we do like before, 7 times 1 is 7, 7 times 2 is 14. And we see that the 7 is contained 2 times in the 14. So we write the 2 in the result next to the 1. So 12 is the result, and we put the 14 below the other 14. Then we do a subtraction. 4 minus 4 is 0, and 1 minus 1 is 0. So the 0 represents the remainder. So 84 divided by 7 is 12, which is the result, and the remainder is 0. The 12 is the quotient. Operation properties. A property of an operation in math is a characteristic or rule that defines how the operation interacts with numbers. These are the 7 properties of operations: commutative, associative, dissociative, distributive, invariant, inverse, and identity. Commutative property. The commutative property states that changing the order of numbers in an operation does not change the result. Here we have an example with addition and one with multiplication. So here we have the formula a plus b is the same as b plus a, where a and b represents numbers. So this means that if we do a plus b or we do b plus a, it's the same thing. For multiplication, if we do a times b or if we do b times a, it's the same thing. So here we have 2 plus 3, and here we have 3 plus 2. 2 plus 3 is 5, and 3 plus 2 is also 5. So changing the addends does not change the result. Whether we do 2 plus 3 or 3 plus 2, the result will always be 5. Here we have 2 plus 3 equals 5, and 3 plus 2 equals 5. For multiplication, we have 4 times 3, and here we have 3 times 4. 4 times 3 is 12, and 3 times 4 is also 12. So whether we do 4 times 3 or 3 times 4, the result remains 12. Associative property. The associative property states that the way numbers are grouped in an operation does not change the result. Here we have a plus b in parentheses plus c, and here we have a plus in parentheses b plus c. So here we have 2 plus 3 in parentheses plus 4, while here we have 2 plus in parentheses 3 plus 4. 2 plus 3 is 5, plus 4 is 9. And here 3 plus 4 is 7, 2 plus 7 is 9. whether we group it in this way or in this way, it doesn't change the result. Here we have 4 times 3 in parentheses times 2, and here we have 4 times in parentheses 3 times 2. So 4 times 3 is 12, times 2 is 24. Here we have 4 times, in parentheses we have 3 times 2, which is 6. So 4 times 6 is 24. So the result doesn't change. Dissociative property. The dissociative property is an algebraic property derived from addition and multiplication. It establishes that in an addition or multiplication, it is possible to replace an addend or a factor with two addends or two factors whose sum or whose product coincides with it. So here we have a plus b, and here we have a plus in parentheses c plus d if b equals c plus d. So pretty much what we did is we replaced the b with c plus d. For multiplication we did the same, a times b, and we replaced this b with c times d. Here we have 5 plus 7, and here we have 5 plus 4 plus 3. So we replace this 7 with 4 plus 3, which is still 7. 5 plus 7 is 12, and 5 plus, in parentheses, 4 plus 3, which is still 7, equals to 12. For multiplication, 4 times 6, we have rewritten this 6 as 2 times 3. 4 times 6 is 24. 4 times, in parentheses, 2 times 3 is still 24. Invariant property. The invariant property states that for both subtraction and division, if you apply the same number to both sides of an equation, the equality remains unchanged. So here we have a minus b, and here we have in parentheses a plus c minus in parentheses b plus c. So what we did is that we added to both a and b the c. While for division, a divided by b, we multiplied both a and b by c. Here we have 5 minus 3, and here we added 2 to both 5 and 3, so 5 plus 2 and 3 plus 2. 5 minus 3 equals 2. 5 plus 2 is 7, and 3 plus 2 is 5. 7 minus 5 equals 2. So the result doesn't change. 12 divided by 6, and here we multiply both 12 and 6 by 3. So 12 times 3 and 6 times 3. 12 divided by 6 equals 2. And 12 times 3 is 36, and 6 times 3 is 18. So 36 divided by 18 is 2. So the result doesn't change. Distributive property. The distributive property states that multiplying or dividing a number by a group of numbers added together is the same as doing its multiplication or division separately. So here we have a times, in parentheses, b plus minus c. The plus minus sign means that we can use both plus and minus. We can replace it with either plus or minus. It's the same as a times b plus minus a times c. And for division, a plus or minus b divided by c, which we have written as a divided by c plus minus b divided by c. 5 times 4 plus 3. And here we have done 5 times 4 plus 5 times 3. So here we done 4 plus 3 is 7. 5 times 7 equals 35. And here we did 5 times 4 equals 20, plus 5 times 3 equals 15. 20 plus 15 equals 35. The result is the same whether we do the addition first in parentheses or if we separate the calculations in multiple multiplications. 4 plus 3 is 7, and while here the result is still 35. 4 plus 6 divided by 2, and here we did 4 divided by 2 plus 6 divided by 2. 4 plus 6 is 10, 10 divided by 2 is 5. 4 divided by 2 is 2, and 6 divided by 2 is 3. 2 plus 3 equals 5. So the result doesn't change. Identity property. The identity property states that any number combined with its identity element remains unchanged. So here we have addition, a plus 0 equals a. So 0 is the identity element for addition. If we add a 0 to a number, we get the number itself. So 7 plus 0 is equal to 7. For subtraction, it's the same thing. A minus 0 equals to a. So we did 3 minus 0 is still equals to 3. The identity element for subtraction is also 0, like addition. Multiplication, a times 1 equals a, 8 times 1 equals 8. So for multiplication, the identity element is 1, it's not 0. If we would do 8 times 0, it would be 0. So 1 is the identity element for multiplication. For division, is also 1, the identity element. A divided by 1 is a. 9 divided by 1 equals to 9. So like for multiplication, the identity element of division is 1. Inverse property. The inverse property states that combining a number with its inverse results in the identity or neutral element. For addition, we did a plus minus a equals 0. So plus and minus is the same as doing minus. So a minus a equals 0. So 7 plus minus 7. So 7 minus 7 equals 0. So we got 0, which is the identity element. Subtraction, a minus a equals 0. So we did 3 minus 3 equals 0, like for addition. Multiplication, we did a times 1 divided by a. So this is a fraction. Equals 1 for a not equal to 0. So here in the example, we did a times 1 8. We simplified it to 8s. So they cancel to 1. Then we multiply the remaining 1 by 1, giving 1. For division, a divided by a equals 1. For a not equal to 0, so 9 divided by 9 equals to 1. This is a summary table of the properties and what operation they are associated with. So here, for example, for the commutative property, we can see where there is a check mark. It means that it exists, and it exists for addition and multiplication, but it doesn't for subtraction and division. Or you can read it in a vertical way. So for the operation addition, we have the commutative property, the associative, the identity, the inverse, the dissociative. But we don't have the distributive and the invariant. Here are the formulas of the properties. Negative numbers. Negative numbers are numbers less than 0, indicated by a minus sign. They represent values below 0 in the number line. This below is the number line. To the right of 0 are the positive numbers, and to the left of the 0 are the negative ones, the one less than 0. Here in the number line, I represented positive numbers up to 10 and negative up to negative 10, but there are infinite numbers in both directions. Addition with negative numbers. Adding a negative number is the equivalent of subtraction. 5 plus, in parentheses, negative 3 equals to 5 minus 3 equals 2. Because positive times a negative equals a negative. So for this reason, we do a subtraction. On the number line, we start from 5 and we take 3 steps back to 2. Addition between negative numbers. When you add two negative numbers, add their absolute values and keep the negative sign. Absolute value means we are adding the number itself without any sign. So it's like it's a positive number. Because without a sign, we implicitly consider it a positive number. Negative 5 in parentheses plus negative 3 in parentheses equals to the negative sign outside, and we sum the numbers inside the parentheses. So negative, and in parentheses 5 plus 3 equals to negative 8. Adding two negative numbers gives us another negative number. On the number line, we start from negative 5 and we move left of 3 because we have added negative 3 and we get to negative 8. Subtraction with negative numbers. Subtracting a negative number is the equivalent of addition. 5 minus negative 3 in parentheses equals to 5 plus 3 equals 8. Negative times negative results in positive. We will see why later. On the number line, we begin at 5, then move 3 units to the right, adding plus 3, landing on 8. Subtraction between negative numbers. When you subtract two negative numbers, you add the absolute value of the subtrahend to the minuend. The minuend is the first number, so the negative 5 in this case, and the subtrahend is the second number, so the negative 3 in this case. Here we have negative 5 in parentheses minus in parentheses negative 3 equals to negative 5 plus 3. This is because a negative times another negative equals to a positive. So negative 5 plus 3 equals to negative 2. On the number line, we start from negative 5 and move to the right because we've added 3. So negative 5 plus 3 equals to negative 2. Multiplication and division with negative numbers. Negative numbers follow specific rules when multiplied and divided. A positive number multiplied by a negative number, or a negative number multiplied by a positive number, gives a negative result. 5 times negative 3 equals to negative 15. Negative 6 divided by 2 equals to negative 3. So here we have 5, which is a positive number. And here we have 2, which is also positive. And then we have these two negative numbers. Even if we have not written the plus sign next to the 5, it is implicit that it is a positive number. So here we have a positive number, the 5, times a negative number, the negative 3, equals to negative 15. So a positive and a negative, and we get a negative result. While here we have a negative, and we have a positive, and we have a negative result. A negative number multiplied by a negative number gives a positive result. Negative 5 times negative 3 equals to plus 15. Here I've written this plus, but it was not necessary. Negative 6 divided by negative 2 equals to plus 3. So in this case, we have both negative numbers and we get a positive result. Why? Why a positive number times a negative number gives us a negative result? When you multiplied a positive number by a negative number, you are essentially changing the direction. Multiplying by a negative number means reversing the sign of the result. 2 times negative 3 equals to negative 6. On the number line, we start from the number 2, we get 6, and then we change direction, and we get to negative 6. In a distributive property, so the distributive property, A times, in parentheses, B plus C equals to A times B plus A times C. Now let's use specific values. A equals 1, B equals 1, and C equals negative 1. Based on the distributive property, here we have just replaced the letters with the values that we have assigned to them. So based on distributive property, 1, which is the A, this red one is the A, the blue is the B, and the green is the C. So 1 times, in parentheses, 1 plus, in parentheses again, negative 1, close parentheses, equals to 1 times 1 plus 1 times negative 1. Simplifying inside parentheses, here we add 1 plus negative 1, so it is a subtraction. It's 1 minus 1, so it's 0. So here we have 1 times 0, which is 0. And here we've done 1 times 1, which is 1. And we kept this as it was. Therefore, 0 equals to 1 plus 1 times negative 1. To make this true, 1 times negative 1 must be negative 1. 0 equals to 1 plus negative 1. This is an equation, so both sides of the equation must be equal, must be true, so they both must be 0. In order to make both sides 0, we need the 1 times negative 1 to be negative 1. So finally we got 0 equals to 1 plus negative 1. So plus and negative is negative. So it's 1 minus 1. So it is 0. Why negative times a negative equals a positive? Why does multiplying two negative numbers yield a positive result? When we multiply two negative numbers, you can think of it as negating a negative. That results in a positive. The negative sign can be seen as a change of direction. If you change direction twice, you return to your original position. Negative 2 times negative 3 equals plus 6. We start at negative 2 on the number line. Multiplying by 3 reverses our direction and moves us 3 steps of length 2 to the right, landing at plus 6. Here we have the distributive property again. Let's now use specific values. A equals negative 1, B equals 1, C equals negative 1. And we substitute these values into the distributive property. Based on the distributive property, we get this. Simplifying inside parentheses, we get this. Minus 1 times 0 is 0. Therefore, 0 equals negative 1 plus, in parentheses, negative 1 times negative 1. For this equality to hold, negative 1 times negative 1 must equal plus 1. We require both sides of the equation to yield the same value, namely 0, so that the distributive law remains valid. So we do negative 1 plus 1 is equal to 0. So 0 equals to 0. Factors. Factors are numbers that are divided into exactly one other number. They are like bricks that make up a larger number. Factors of 12, 1, 2, 3, 4, 6, 12. These numbers can be multiplied together to get 12. If we take 6 for example and calculate 12 divided 6, we get 2 with remainder 0. So the 6 is divided exactly into 12. So 6 is a factor of 12. If we take another number, for example 5, 12 divided by 5 is 2.4. So 5 doesn't divide into 12 exactly, so it's not a factor of 12. Factors of 15, 1, 3, 5, 15. These numbers can be multiplied together to get 15. If we divide 15 by 5, we get 3 with remainder 0. We prove that 5 is a factor of 15. And if we multiply these numbers together, so if we do like 3 times 5 is 15. If we do 1 times 15, we get 15. So these numbers can be multiplied together to get 15. Multiples. Multiples are the results of multiplying a number by an integer. They are like the family of numbers linked to a specific number. Multiples of 5, 5, 10, 15, 20, 25, 30, and so on. These numbers are obtained by multiplying 5 by various integers. So these are the numbers you get if you multiply 5 by various integers. So for example, 5 times 1 is 5, 5 times 2 is 10, 5 times 3 is 15, and so on towards infinity. Multiples of 7. 7, 14, 21, 28, 35, 42, and so on. These numbers are obtained by multiplying 7 by various integers. As before, if we multiply 7 by various integers, we get its multiples. 7 times 1 equals to 7, 7 times 2, 14, 7 times 3, 21, and so on towards infinity. Even. Even numbers are integers that can be divided by 2 without leaving a remainder. They can be represented as 2n, where n is an integer. Example: 2, 4, 6, 8, 10. These are all even numbers. For example, 10 divided by 2 equals 5 with remainder 0. It can be represented as 2n, where n is 5, so 2 times 5 equals 10. Even numbers are of the form 2n. If we take any integer and replace it with n, we get an even number. If the digit of the units is 0, 2, 4, 6, or 8, then the number is even. If we take the number 20, the digit of the units is 0, so 20 is an even number. Or for example, if we take the number 44, the digit of the units is 4, so 44 is an even number. Odd. Odd numbers are integers that cannot be divided by 2 without leaving a remainder. They can be represented as 2n plus 1, where n is an integer. Example: 1, 3, 5, 7, 9. For example, the number 5 divided by 2 equals 2.5. So the quotient is 2 with remainder 1. We have a remainder, so 5 is an odd number. Odd numbers can be represented in the form 2n plus 1. So for example, if we substitute the number 2 for n, we get 2 times 2 plus 1. 2 times 2 is 4 plus 1 equals 5. So 5 is an odd number. If the digit of the units is 1, 3, 5, 7, or 9, then the number is odd. For example, the number 41, the digit of the units is a 1, so 41 is an odd number. Or for example, the number 57, 57, the digit of the units is a 7, so 57 is an odd number. Odd and even numbers rules. For addition, if we sum two even numbers together, we get an even number. So 2, which is even, plus 4, which is also even, 2 plus 4 equals 6, which is even. If we sum together two odd numbers, we get an even number. 3 plus 5, which are both odd numbers, equals to 8, which is even. If we sum an even and an odd number, we get an odd number. 2 is even, plus 3, which is odd. 2 plus 3 equals 5, which is an odd number. Subtraction. If we subtract two even numbers, we get another even number. 8 minus 4 equals 4. If we subtract two odd numbers, we get an even number. So 7 minus 5, which are both odd, equals to 2, which is even. If we subtract an even and an odd number, we get an odd number. 6, which is even, minus 3, which is odd, equals to 3, which is odd. If we add odd as a minuend and even as a subtrahend, we get an odd number. 9, which is odd, minus 2, which is even, equals to 7, which is odd. Multiplication. If we multiply together two even numbers, we get an even number. So 2 times 4 equals 8. If we multiply together two odd numbers, we get an odd number. 3 times 5 equals 15. If we multiply an even and an odd number, we get an even number. 2 times 3 equals 6. Division. If we divide two even numbers, we may get an odd or an even number. So 8 divided by 4, which are both even numbers, equals to 2, which is an even number. 6, which is even, divided by 2, which is even, equals to 3, which is odd. If we divide two odd numbers, we get an odd number. So 9 divided by 3 equals to 3. If we divide an even by an odd number, we get an even if divisible. So 6, which is even, divided by 3, which is odd, equals to 2, which is even. While here 6 divided by 5 equals to 1.2. This is not even an integer. And if we divide an odd by an even number, we don't get an integer. So 9, which is odd, divided by 2, which is even, equals to 4.5, which is not an integer. The overall rule is that if in a number the digit of the units ends with 0, 2, 4, 6, or 8, the number is even. Otherwise, if the digit of the units ends with 1, 3, 5, 7, or 9, the number is odd. Prime numbers. Prime numbers are numbers greater than 1 that have no divisors except 1 and themselves, which means they have only two factors. Factors of 7, 1 and 7 cannot be divided evenly by any other number. So let's remember the definition of factors. Factors are numbers that divide perfectly into another number, that is, without leaving any remainder. For example, the number 4 is a factor of 12, as are 2, 6, and 3. Instead, consider the number 7. The only numbers that divide perfectly into 7 are 1 and 7 itself. These numbers, divisible only by 1 and by themselves, are called prime numbers. So, if you look at 7, the only numbers that can divide perfectly into 7 are 1 and 7 itself. So, there are no other numbers that can divide evenly into 7. If you try with 2, 7 divided by 2 is 3.5. So it's 3 with a remainder of 1. It's now a factor. So 7 has only 1 and 7. So it's called a prime number. Prime numbers are not just a mathematical curiosity, but have important applications. For example, they're used in cryptography to protect data, such as in online payments, and in computer science for hash functions or efficient algorithms. Composite numbers. Composite numbers are numbers greater than 1 that have more than 2 divisors. They therefore have more than 2 factors. Factors of 8, 1, 2, 4, and 8. can be divided evenly by numbers as well as 1 and 8. So 8 is not a prime number, because its factors are not only 1 and itself, 8, but 8 also has 2 and 4. So the numbers that have more than 2 factors are called composite numbers. If it would have only 1 and 8, it would have been a prime number, but if it has more than 2 factors, more than just 1 and itself, then it is a composite number. Fractions. A fraction represents a part of a whole. It consists of a numerator, the top number, representing the considered part, and a denominator, the bottom number, representing the whole or total number of parts. What you see is a fraction. We have two numbers separated by a horizontal line. This fraction is read as 1/6, which corresponds to 1 part out of 6. The number above the line, 1 in this case, is called the numerator. The number below the line, in this case 6, is called the denominator. Here we have a pizza cut into 6 slices. The whole pizza corresponds to 6/6, or 6 parts out of 6. Here we have highlighted in black a slice of the pizza, which therefore corresponds to a sixth, which is our fraction here. If we take 2 slices into account, we have 2/6, 2 parts out of 6. If you add another 1/6, you get 3/6, which is half the pizza. With 6/6, we have the whole pizza. If you think about it, 6/6 represent the whole pizza. It is as if the pizza had never been cut, or rather, we consider it in its entirety and not in slices. Dividing the number above, the numerator 6, by the number below, the denominator 6, we get 1. This one corresponds to the whole pizza. Types of fractions. Proper fractions. Numerator less than the denominator. So 3, the numerator, is less than the denominator 4. Improper fractions. Numerator greater or equal than the denominator. So the numerator 5 is greater than the denominator 3. Mixed fractions. Integer and proper fraction. So here 1 is the integer and 1/2 is the proper fraction, this one here. Which of these pizza slices is the biggest? A slice from the pizza on the left or 2 slices from the pizza on the right? Pause the video if you want more time to think. They are the same. Different cuts, same amount. The slice on the left is 1/3, 1/3. The slices on the right are 2/6. If we simplify 2/6, we get 1/3, exactly like the other pizza. So, the 2 slices on the right correspond to the 1/3, just like the single slice on the left. Equivalent fractions. These fractions represent the same quantity. Even if the circles have been divided into a different number of parts, its fraction represents half of the circle. We have a circle divided in 2 parts, with an half colored green. Another circle is divided into 4 parts, with 2 colored segments. Then, one divided into 6 parts, where we color 3 of them. Finally, a circle into 8 parts, with 4 colored segments. Even if the circles are divided differently, all these fractions indicate the same quantity. So for all of these circles and all these fractions, they all represent half of the circle. Greatest common divisor, GCD. The greatest common divisor, GCD, is the largest number that divides 2 or more integers without leaving a remainder. It is the biggest factor they share. If we remember, factors are numbers that divide other numbers exactly, so without leaving a remainder. Find the GCD between 4 and 6. The factors of 4 are 1, 2, 4. So because if we take 2, for example, 4 divided by 2 is 2, with the remainder 0. So there is no remainder, so 2 is a factor of 4. The factors of 6 are 1, 2, 3, 6. So we have to pick the biggest factor that they share, and the biggest factor that they share is 2, because 2 is both a factor in 4 and in 6, and it's their largest factor that they share. The greatest share factor is 2. Therefore, 2 is the greatest common divisor between 4 and 6. Least common multiple, LCM. The least common multiple, LCM, is the smallest number that is a multiple of 2 or more numbers. It's the smallest number into which each of the numbers can divide evenly. If we recall, multiples are the numbers we get by multiplying a number by an integer. Find the LCM between 4 and 6. The multiples of 4 are 4, 8, 12, 16, 20. To get the multiples of 4, we did 4 times 1, 4, 4 times 2, 8, and so on. The multiples of 6 are 6, 12, 18, 24, and so on. The smallest shared multiple between 4 and 6 is 12. So 12 is the least common multiple between 4 and 6. Adding and subtracting fractions. Here we have 1/3 plus 1/6. And we want to know how to add them together. First of all, we need to find the least common multiple, LCM, between 3 and 6, which are the denominators of our fractions. The multiples of 3 are 3, 6, and 9. The multiples of 6 are 6, 12, and 18. The LCM between 3 and 6 is 6. Then we need to adapt the fractions. So we found the LCM, which is 6, and we need to adapt both fractions to 6. So both denominators must be 6. So in this fraction, we have a 1/3, we have a 3 in the denominator. So we do 6 divided by 3. 6 is our LCM. 6 divided by 3 is 2. We need to multiply both the numerator and denominator by 2. So 1 times 2 is equal to 2. 3 times 2 is 6. So this 1/3 has become 2 over 6, while 1/6 already has the denominator at 6, therefore remains unchanged. So we don't have to adapt this fraction here because we already have 6 in the denominator. Sum the numerators. So here we have rewritten 1/3 into 6. So we do 2 over 6 plus 1 over 6. We can add them together because they have the same denominator. So 2 plus 1 equals to 3 over 6. Simplify the result if possible. So we have divided both 3 and 6 by 3, and we got 1/2. So 1/3 plus 1/6 is equal to 1/2. This is another method of solving the sums and subtraction between fractions. The procedure is basically the same, but the only difference from before is that here we don't adapt the fractions. We do the calculation all at once. So here we still find the least common multiple, which is 6. And here we divide the LCM by the denominator and multiply by the numerator. So we had 6, which is our LCM, and divide it by the denominator of the first fraction, and we multiply it by the numerator. So we had 6 divided by 3 times 1 plus 6, which is our LCM, divided by the denominator of the second fraction times 1, which is the numerator of the second fraction. 6 divided by 3 is 2 times 1 is 2, plus 6 divided by 6 is 1 times 1 is 1. So 2 plus 1 equals to 3. Then we simplify. In both ways, we get the same result. Simplifying fractions. Simplifying fractions means reducing them to their simplest form by dividing both the numerator and the denominator by their greatest common divisor, GCD, so that the numerator and denominator have no common factors other than 1. If we remember, factors are numbers that divide other numbers evenly, so without leaving a remainder. So here we have 6/8. So the factors of 6 are 1, 2, 3, and 6. So factors are numbers that divide 6 evenly without leaving a remainder. So for example, 6 divided by 2 is 3, with remainder 0. And the factors of 8 are 1, 2, 4, and 8. So 8 divided by 2 is 4 with remainder 0. And the GCD between 6 and 8 is 2 because we're looking for the biggest share factor. And the biggest share factor between 6 and 8 is 2. Yeah, the numbers are different except for the 1, but 2 is larger. And so that's the biggest factor share between 6 and 8. So we will divide both 6 and 8 by 2. And we get 3/4. If we try to look for the largest factor share between 3 and 4, now it would be 1. So the factors of 3 are 1 and 3. The factors of 4 are 1, 2, and 4. The GCD between 3 and 4 is 1. Because that's the largest share factor, we can't simplify this fraction any further. If we divide 3 by 1, it's always 3, and 4 divided by 1 is 4. So they give us back the numbers themselves. So we are unable to simplify this further. We simplified 6/8 in 3/4. The fraction maintains the same value. To show this, let's consider two circles. One divided into 8 parts with 6 colored segments, and one divided into 4 parts with 3 colored segments. As we can see, the colored part is identical in both circles, showing that simplification does not alter the value of the fraction. Both represent the same portion. Here we have a circle divided into 8 parts, and we color 6 of them, while here we have a circle with 4 parts, and we color 3 of them. As we can see, the colored parts in both circles are the same. So 6/8 and 3/4 is the same fraction, and it represents the same quantity. Multiplication of fractions. To multiply fractions, multiply the numerators together and the denominators together. 2/3 times 4/5. The numerators are the numbers above the line, so 2 and 4, while the denominators are those below, so 3 and 5. We multiply the numerators 2 and 4 to get 8, and we multiply the denominators 3 and 5 to get 15. Division of fractions. To divide fractions, multiply the first fraction by the reciprocal of the second fraction. The reciprocal of a number is that number written as 1 divided by that number. For example, the reciprocal of 4/5 is obtained by reversing the fraction. The numerator becomes the denominator and vice versa. But why do we turn a division into multiplication by using the reciprocal? Because dividing two fractions is really asking how many times does the second fraction fit into the first. Using the reciprocal makes this easy. It lets us compare the two values by multiplication, which is usually more straightforward to compute than doing the division directly. We have written the reciprocal of 4/5, which is 5/4. And now we multiply 2/3 by 5/4. Then we multiply the numerators between them, 2 times 5, and multiply the denominators between them, 3 times 4. So we reverse 4/5 to 5/4, and now we multiply across. 2 times 5 and 3 times 4. So the division 2 over 3 by 4 over 5 results in 10 over 12. Let's simplify 10 over 12 by dividing both sides of the fraction by 2 to get 5 over 6. Going back, we could have simplified the numerator 2 and the denominator 4 by dividing both by 2, obtaining 1 in the numerator and 2 in the denominator. That would have led us directly to the final result, 5 over 6. Instead of simplifying later, we simplified first and got the same result, 5 over 6. Rationalization. Rationalizing a fraction means converting a fraction with a radical in the denominator into an equivalent fraction without a radical in the denominator. To do this, that is, to remove the radical from the denominator, we will have to multiply this fraction with another that has the same radical in both the numerator and the denominator. But why do we want to remove the radical from the denominator? Leaving a radical in the denominator makes calculation less practical and sometimes more complicated, especially when you have to add or compare fractions. By multiplying by a fraction that eliminates the radical in the denominator, we get a simpler, more standard form to represent the result. It is acceptable to leave a radical in the numerator because it does not adversely affect the clarity or calculation of the fraction. So here we have 1 in the numerator and the square root of 2 in the denominator. So we multiply by the square root of 2 both in the numerator and in the denominator. Above we get square root of 2 in the denominator because of the property of square roots. Multiplying two roots with the same radicand, the result is the rootless radicand. So the square root of 2 times the square root of 2 gives us 2 without the square root. The end result is the square root of 2 in the numerator and 2 in the denominator. Mean. The mean, also known as the arithmetic mean or average, is a measure of central tendency in a set of numbers. It is calculated by adding all the values and dividing by the number of values. Example. Calculate the mean of 5, 8, 10, and 12. So we did 5 plus 8 plus 10 plus 12 divided by 4 equals to 8.75. We divide by 4 because there are 4 numbers, 5, 8, 10, and 12. Applications of the average. Calculate grades. For example, we can use it to calculate grades. Grade 1 is 7, grade 2 is 9. The mean is 7 plus 9 divided by 2 because there are 2 grades, equals to 8. 7 plus 9 is 16, divided by 2 is 8. Average speed, speed 1 is 15 kilometers per hour. Speed 2 is 45 kilometers per hour. 15 plus 45, which is 60, divided by 2 because there are 2 speeds, equals to 30. Average temperature, temp 1 is 20 degrees Celsius, temp 2 is 25 degrees Celsius, 20 plus 25 is 45, divided by 2, because there are two temperatures, equals to 22.5. Weighted average. A weighted average is an average calculated by assigning specific weights to individual values that correspond to their relative importance within a collection of values. Example: calculate the weighted average of grades of the following exams. Exam 1 is worth 30% and exam 2 is worth 70%. The grade of exam 1 is 8.5, which is worth 30%, and the grade of exam 2 is 6, which is worth 70%. So 0.3, which is the 30%, times 8.5, which is the grade of exam 1, plus 0.7, which is the 70%, times 6, which is the grade of the second exam, equals to 6.75. Median. The median is the central value in a set of numbers when they are arranged in order. Example: arrange the numbers in order if they are not already. 3, 5, 7, 9, and 11. As we can see, in this case, the numbers are arranged in order from the smallest to the largest. And as we can see, the central value of these numbers is the number 7. The median number is 7 because it is in the center. Example: arrange the numbers in order 2, 4, 6, and 8, which are already in order. Since there are two median numbers, 4 and 6, the median is the average, is the mean of these two numbers. 4 plus 6, which is 10, divided by 2, because there are two numbers. There are 4, but we're considering only 4 and 6. So 10 divided by 2 equals to 5. So the median is 5. Powers. A power, or exponent, or index, is a number that indicates how many times a base number is multiplied by itself. For example, 2 multiplied by itself 3 times, 2 times 2 times 2 equals 8, can be rewritten as 2 raised to the power of 3. This reads 2 raised to the power of 3, or 2 raised to the third power, or 2 cubed. The name cube in 2 cubed comes from the geometry of a cube and how its volume is calculated, because a number raised to the third power is like calculating the volume of a cube. The volume being the amount of space in a 3D object. The exponent 3 indicates how many times the base 2 must be multiplied by itself, in this case 3 times. Writing 2 raised to the power of 3 is the exact same thing as writing 2 times 2 times 2. The number 2 is called the base, and the number 3 is called the exponent. So writing 2 to the third power is a more compact way of writing this multiplication here. 2 times 2 times 2. Typical mistakes. Now let's look at some typical mistakes that are made when calculating powers. Here we have the number -3 raised to the second power. Here it says -3 to the second power equals to 9. This is wrong. One might think that -3 to the second power corresponds to -3 multiplied by -3, both in parentheses. We know that a negative number multiplied by another negative number results in a positive number. But in this case, it is wrong to calculate the -3 to the second power in this way. -3 to the second power equals to -9. Because -3 squared is calculated in this way. The number 3 is repeated, but the negative sign remains outside this repetition. We only repeat the number, not the sign. So we calculate 3 times 3 in parentheses with a negative sign outside, since it is not repeated. This gives us 9, and with a negative sign it becomes -9. So -3 to the second power gives us a result of -9. This is the correct result. To obtain the operation -3 times -3, we have to put both 3 and the minus sign in parentheses. Here we have the exponent 2 above the entire parenthesis, which includes both the minus sign and the 3. So let's calculate -3 in parentheses altogether raised to the second power, which is equal to, in parentheses, -3 times in parentheses -3, which is equal to 9, because two negative numbers multiplied together make a positive number. A negative times another negative equals a positive. Another typical mistake is to calculate 3 to the second power equals to 6. This is wrong. We're not doing 3 times 2. The number 2 indicates the number of times the number 3 must be multiplied by itself. So we're doing 3 times 3, which is equal to 9. Three to the second power is equal to 3 times 3, which is 9. 3 times 3 is the same as doing 3 plus 3 plus 3, which is equal to 9. Another typical mistake is to think that a negative exponent gives us this type of result. 2 raised to the power of -3 is equal to -8. This is wrong. A negative exponent indicates that we have to calculate the reciprocal of the number with a positive exponent. This happens because a negative exponent means reversing the multiplication of the base. For example, with 2 raised to the power of -3, we do the reciprocal of 2 to the third power. 1/2 to the third power. We solve 2 to the power of 3, which is 8, and we get 1/8. This is a summary table of the typical mistakes that are made in powers. In red, the mistakes, and in green the correct calculations. Multiplication and division with exponents. Here we have 2 to the third power times 2 to the second, or 2 squared. We could first calculate 2 to the power of 3, which equals to 8, separately, and then calculate 2 to the second power, which equals to 4. And then multiply them together. 8 times 4 equals 32. But there is an easier way. When we multiply powers with the same base, we add up the exponents. This happens because each exponent represents how many times we multiply the base by itself. So, adding the exponents is equivalent to combining all multiplications into a single power. For example, with 2 to the power 3 times 2 to the power 2, we have 2 times 2 times 2 multiplied by 2 times 2. In total, there are 5 factors of 2. So the base remains 2 and the exponent becomes 5, 2 to the 5th power. So 2 to the 3rd power times 2 to the 2nd power gives us 2 to the 5th power by adding the exponents. 3 and 2, 2 to the 5th power equals to 32. 2 times 2 5 times get us 32. 2 to the 3rd power divided by 2 to the 2nd power. In multiplication, we added the exponents. In division, we subtract them. So let's do 2 to the power of 3 minus 2 equals 1. 2 to the 3rd power divided by 2 to the 2nd power is equal to 2 to the 1st power. 2 to the 1st power is equal to 2. Product rule. When you multiply two powers with the same base, you add the exponents. A to the power of m times a to the power of n equals a times m plus n, where a is the base and m and n are the exponents. 3 to the power of 4 times 3 to the power of 2 equals to 3. 3 to the power of 4 plus 2 equals 3 to the power of 6. As we have seen before, we use this rule to get the result. Quotient rule. When you divide two powers with the same base, you subtract the exponents. A to the power of m divided by a to the power of n equals to a to the power of m minus n. 3 to the power of 4 divided by 3 to the power of 2 equals to 3 to the power of 4 minus 2, which equals to 3 to the power of 2. Power rule. When one power is raised to another power, the exponents multiply. A to the power of m in parentheses all raised to the power of n is equal to a to the power of m times n. 3 to the power of 4 in parentheses all raised to the power of 2 is equal to 3 to the power of 4 times 2, which equals to 3 to the power of 8. Negative exponent rule. A negative exponent represents a reciprocal. A to the power of negative n equals to 1 divided by a to the power of n. 3 to the power of negative 2 equals to 1 divided by 3 to the power of 2. Why a number raised to negative n equals 1 divided by a to the power n. When you raise a number to a negative exponent, you get the reciprocal or inverse of that raised number to the corresponding positive exponent. This happens because negative exponents represent division rather than multiplication. Here we have a to the power of 3, which equals to a times a times a. Here we have a to the power of 2, which is a times a, or it can also be written as a to the power of 3 divided by a. And we have a to the power of 1, which is a, which we can also write as a to the power of 2 divided by a. So here we have a to the power of negative 3, which equals to a to the power of negative 2 divided by a, which is equal to 1 divided by a to the power of 2 divided by a, which equals to 1 divided by a to the power of 3. Then we have a to the power of negative 2, which equals to 1 divided by a to the power of 2. A to the power of negative 1 equals to 1 divided by a. And finally, we have a to the power of 0, which equals to 1. Or we can also write it as a to the power of 1 divided by a. Zero exponent rule. Any non-zero base raised to the power of 0 is equal to 1. A raised to the power of 0 equals 1. 3 raised to the power of 0 equals 1. Why a number to the power of 0 equals 1? Any non-zero number raised to the power of 0 is equal to 1 because it follows the patterns observed in the properties of the exponents. In particular, when you decrease the exponent by 1, you divide by the base. Continuing this pattern, when the exponent reaches 0, the result is 1. For the property a to the power of m times a to the power of n equals a to the power of m plus n. For m equals 1 and n equals negative 1, we replace the values. So we replace 1 where there was m and negative 1 where there was n. And we got a to the power of 1 times a to the power of negative 1 equals to a to the power of 1 plus negative 1, which equals a to the power of 0. Simplifying a to the power of 1 times a to the power of negative 1, we add this and a to the power of 1 is like a fraction with the denominator at 1. So we divide this by the denominator a. So a divided by a is 1. Therefore, a to the power of 0 equals 1. Exponent rules. Here we have summarized the rules of the exponents. Order of operations. The order of operations is the sequence in which mathematical operations, addition, subtraction, multiplication, and division must be performed to ensure consistent and correct results. Order rules. The rules of operations state that the calculations must be performed in this order. Firstly, we need to solve parentheses, then exponents, then multiplication and division from left to right, and finally addition and subtraction from left to right. Here, for example, we have 2 plus 3 in parentheses times 4. So this is a parenthesis, even though there is addition, which is the last one. There is a parenthesis, so this is what we have to do first, and then we do the multiplication. And so here I've written 1 because it is a parenthesis and must be done first. And then we have 3 because it is a multiplication and division. So firstly we do the parenthesis and then the multiplication. So if we calculate 2 plus 3 is 5 times 4, 20. Here we have 8 minus 3 plus 5. So it's addition and subtraction. And we have to do them from left to right. So firstly we do the subtraction, 8 minus 3, and then we add 5. Eight minus 3 equals 5. 5 plus 5 equals 10. If we would have performed this operation in another way, like 3 plus 5 first, it would have been 8 minus 8 equals 0. Result would have been different and wrong. So this is the way. Firstly, the subtraction, because it's on the left, and then we do the addition. 5 plus 3 minus 2 to the third power. 2 to the third power is a power, therefore exponents, and for this reason it has the priority over addition. So first we calculate 2 to the power of 3, and then the addition. So 2 to the power of 3 is 8, and 5 plus 3 is 8, so 8 minus 8 equals 0. Here we have 6 divided by 2 times, in parentheses, 1 plus 2. Here we have a parenthesis, so we first calculate what's inside the parenthesis, and then we move on to the division. So here we calculated what's inside the parenthesis. 1 plus 2 is 3. We have multiplication and division from left to right. So firstly we do 6 divided by 2, and then we do times 3. So 6 divided by 2 is 3, times 3 equals 9. Acronyms to remember. What you see here is an acronym, which is an abbreviation formed by the initial letters of other words. This acronym will help us remember the rules of the order of operations. This acronym is called PEMDAS. The P stands for parentheses, E for exponents, M of multiplication, and D for division, A for addition, and S for subtraction. So this acronym, PEMDAS, help us remember the rules. First, we need to calculate parentheses, then exponents, then multiplication division from left to right, and finally addition and subtraction from left to right. Here I put the symbols associated with each operation. This is another acronym, BODMAS. It's pretty much the same as the previous one, but instead of parentheses and exponents, we have brackets and orders. And orders is referring to exponents. So B for brackets, O for orders, division, and multiplication, A and S for addition and subtraction. Here I put an additional acronym in addition to PEMDAS and BODMAS, which is BIDMAS, where instead of exponents or orders, it uses the I for indices, always referring to exponents. So we have brackets and indices. Just pick one of them and stick with it, and you'll be able to remember the rules. Logarithms. Logarithms are the reverse operation of exponentiation. They indicate the exponent to which a number, the base, must be raised to obtain a given number. This is a logarithm. This is the way it is written. We use the word log, followed by a smaller number at the bottom, 10 in this case, and a larger one next to it, 1000 in this case. So this is the log base 10 of 1000. I put a question mark because there is a result here. The number at the bottom next to log, the 10, is called the base. That is the base of the logarithm, while the number in purple, 1000, is called number or argument, the logarithm's argument. To what power does the base 10 need to be raised to produce the given number, 1000? So if we take the base 10 and we raise it to the power of 2, we get 10 times 10, which is 100, so it's not enough. But if we do 10 to the power of 3, so 10 times 10 times 10, we get 1000. The base 10 must be multiplied by itself 3 times to get the number 1000. Ten to the third power, or 10 times 10 times 10, is equal to 1000. So the logarithm base 10 of 1000 is 3. We can avoid writing the base because a logarithm without a base implicitly assumes the value 10. So when you see logarithms without a base, they are supposed to be base 10. In addition, the argument 1000 can also be written in parentheses. Here we have the logarithm on one side and the powers on the other. The two operations are intrinsically connected. These are the formulas of the two operations. Log base b of n equals to x, while for the powers, taking the base b and putting x as the exponent of the base, we get n, which was the argument of the logarithm. If we take the base and we raise it to the result of the logarithm, so 10 to the power 3, we get 1000, which was the argument of the logarithm. Natural logarithm. The natural logarithm, denoted by ln, uses the base e, where e is an irrational constant approximately equal to 2.71828, also known as Euler numbers or Napier number, but mostly is known as the Euler number. So we have log base e. Which we denote as ln. So instead of writing log in base e, we usually write ln to indicate logarithm in base e. With ln, you don't need to specify any base because the base is already e. The natural logarithm ln of e itself is obviously 1. E raised to the power of 1 equals e. The log in base e of e equals 1 because e to the power of 1 equals e. Product property. Product property states that the logarithm of a product is the sum of the logarithms of the factors. The logarithm base b of x times y can also be rewritten as the log base b of x plus the log base b of y. Here we have an example. We have the log base 10 of 2 times 5, and we have rewritten it as the log base 10 of 2 plus the log base 10 of 5. So we calculate the log base 10 of 2, which is 0.301, plus the log base 10 of 5, which is 0.699, and we sum these together and we get 1. We can also see this as from here, if we do the log base 10 of 2 times 5, 2 times 5 is 10, so the log base 10 of 10 equals 1. Because the base 10 raised to the power of 1 get us the argument, which was 10. 2 times 5. Quotient property. The quotient property states that the logarithm of a quotient is the difference of the numerator and the denominator logarithms. Similar property applies to division. The base b logarithm of x over y can be rewritten as the log base b of x minus the log base b of y. This means we can transform a division within a logarithm as a simple subtraction between two logarithms. Here we have an example. We have the log base 10 of 8 over 2, and we have rewritten it as the log base 10 of 8 minus the log base 10 of 2. So we calculate a log base 10 of 8, which is 0.903, minus the log base 10 of 2, which is 0.301, and we got 0.603. We could have also done this division. 8 divided by 2 is 4, so we could also calculate the log base 10 of 4, which is equal to this. Power property. The power property states that the logarithm of a number raised to a power is the power multiplied by the logarithm of the number. So the base b logarithm of x to the power of y can also be written by taking the exponent out, so the y out of the argument, and so it becomes y times log base b of x. So we wrote this exponent outside the argument of the logarithm. Here we have an example, log base 10 of 2 to the third power. We brought this 3 outside of the logarithm, so we brought 3 times the logarithm base 10 of 2. So then we calculated log base 10 of 2, which is 0.301, and we multiplied it by 3, and we got 0.903. Here I show that we could either take out the exponent and calculate the logarithm, or calculate 2 to the third power and calculate the result that in both cases remains unchanged. So whether we do 3 times the log base 10 of 2, or if we calculate log base 10 of 8, 8 because 2 to the power of 3 is 8, in both cases the result is the same. Change of base property. The property of the change of base states that the logarithm of a number in one base can be converted to another base using the ratio of logarithms in the new base. The logarithm base b of x can also be written in a different form as another base. Log base k of x, where k is a different base from b, over log base k of b, where b was our old base. So here we have the log base 2 of 8, and we have rewritten it as the log base 10 of 8 divided by the log base 10 of 2. We calculate log 10 of 8, which is 0.903, divided by the log base 10 of 2, which is 0.301, and we divided this together and we got 3. We can also understand this from the log base 2 of 8. If we raise the base 2 to the power of 3, we get 8. Properties of logarithms. This is a summary of the properties of logarithms. Decimals. Decimals are numbers that have an integer part and a fractional part, separated by a decimal point. They represent fractions in a base 10 system. 1.618. The part before the point, the part of the units in this case, it is called the integer part, while the digits after the point are called the decimal part. These values represent fractions of the unit and indicate how small each digit is after the decimal point. For example, 6 is a tenth, 1 after 6 is 100, and 8 is 1,000. This number reads as 1 0.618. This convention is important for representing numbers accurately, especially in scientific or financial context. Here we have another decimal number, 2.4, where 2 is the integer part and 4 is the decimal part. We had only written 2.4 and not 2.40. When we write 2.4, we imply that the digit after 4, if not specified, is 0. So 2.4 is the same as 2.40 or 2.400. The 4 represents 1/10 of a unit, while the subsequent digits, hundreds and thousands, are implicitly considered to be 0 if not written. This way of writing makes numbers easier to read, but it's important to remember that in scientific or technical contexts, writing trailing zeros may be necessary to indicate the accuracy of the data. Decimal separator. This chart represents the different types of decimal separators used in different countries. The decimal separator is that component that we put between the integer part and the decimal part of a number. In Europe, the comma is mostly used, while in English-speaking countries, the point is mostly used. Knowing these differences is important when reading international data or collaborating with people of other nationalities. In blue, English-speaking countries, the US, the UK, Australia, New Zealand, and then Mexico, a few countries of Africa, a few Southeast Asian countries, and a few other countries in the world. The comma is mostly used in Europe, parts of Africa, South America, Greenland, and a few countries of Southeast Asia, and a few other countries in the world. In this light yellow-green, we have the countries with both and may vary by location or other factors. These are Canada, Peru, and some other countries. In red, we have Arabic decimal separator. And in gray, data unavailable. Anyway, in English-speaking countries, the decimal point is used. Addition and subtraction of decimals. Decimals are added or subtracted by aligning the decimal points and then performing the operation as with integers. Now we add 2.50 plus 3.75. Start from the right. 0 plus 5 equals 5. Next column, 5 plus 7 equals 12. We write down the 2 and carry the 1. Next column, 2 plus 3 plus the carried 1 gives 6. The result is 6.25. Now we want to subtract 5.20 minus 3.18. Start at the rightmost column. 0 minus 8 can't be done, so borrow 1 from the 2 in the tens place. The 2 becomes 1 and 0 becomes 10. 10 minus 8 equals 2. Next column, it is no more 2, it is 1. 1 minus 1 equals 0. Units column, 5 minus 3 equals 2. The result is 2.02. Multiplication of decimals. To multiply decimals, multiply as whole numbers and then count the total number of decimal places in the factors to place the decimal point in the product. We will multiply 1.20 times 3.40. First, ignore the decimal points and multiply the numbers as integers. Multiply 120 times 340. Start with the rightmost digits. 0 times 0 equals 0. 0 times 2 equals 0. 0 times 1 equals 0. So we write 3 zeros. Move to the next row. The 4 in 340. Write a zero shift. Add 1 0 at the end. We add 1 0 because that 4 means 40. So we multiply by 4 and then by 10, i.e. shift the result one place. Then 4 times 0 equals 0. 4 times 2 equals 8. And 4 times 1 equals 4. Write 4,800 under the previous row. Next row, the 3 in 340. Write 2 zero shifts. 3 here means 300, so we shift the result 2 places. Then 3 times 0 equals 0. 3 times 2 equals 6. And 3 times 1 equals 3. Write 36,000. Add the rows 0 plus 4,800 plus 36,000 equals 40,800. Now place the decimal point. Count the decimal places in the original factors. 1.20 has 2 decimal places. 3.40 has 2 decimal places as well. So total 2 plus 2 equals 4 decimal places. Starting from the right of 40,800, count 4 digits. 1, 2, 3, and 4. Here you place the decimal point. So the final result is 4.08. And you can drop the trailing zeros. Division between decimals. To divide decimals, you move the decimal point in the divisor to make it a whole number and do the same shift in the dividend. Then divide it with whole numbers. Here we have 4.5 divided by 1.5. So we write these two numbers without the decimal point. So like they are integers. So we have 45 divided by 15 and we get 3. Operations in decimals. This is a summary table of the decimal operations we've done. Repeating decimal numbers. Repeating decimal numbers, also known as recurring decimals, are numbers that have a decimal expansion that eventually repeats the same sequence of digits ad infinitum. 1 divided by 3 equals to 0.333 indefinitely. Instead of writing 0.333, 3, 3, 3 with a repeating 3, we show this through the symbol above the number 3, this horizontal line. The symbol above the 3 represents a repeating decimal number. 2 divided by 9 equals to 0.222, which we represented with the horizontal line instead of writing 222. Different types of notation. In a table, we have the number in the form of a fraction, and then how the repeating part is shown. We use the vinculum, which is the horizontal line above the repeating part, only the repeating part. Then there is the dot, or the repeating part is enclosed in parentheses. In some countries, the arc is used, and finally the ellipsis, the 3 dots, to indicate that the number repeats and continues indefinitely. Radicals. Radicals are numbers defined by roots with integer indices. They are composed of 3 parts: radical sign, index of the radical, and radicand. The root is the value that, when raised to the power of the index, produces the radicand. This is a radical. It reads square root of 64, or root with index 2 of 64. It is called a square root because, in geometry, the term root refers to the origin or base of a value, and square indicates that the result value represents the side of a square with an area equals to the given number. For example, the square root of 64 is 8, because a square with side 8 has an area of 64. Side times side equals to the area in a square. In blue, the radical sign, the number below, in green, is called the radicand. And the number next to it, to its left, in orange, is called the index. All these elements together, index, radicand, and radical sign, form a radical. The result of the radical is called the root. The square root of 64 is equal to 8, because 8 is that number which raised to the power of 2, that is, multiplied by itself, gives us as result the number under the radical sign, 64. If the index is not present, it is implied that it is 2. This is the most common way to write the square root, so without the index, 2. Radicals and exponents are connected to each other. If we raise the result of the radical, 8, to the index 2, we get the number below the radical sign, the radicand, 64. On one end we have the radical and on the other the exponents. We have a radical to the nth power of a, that is equal to b. If we take b and we raise it to the index n, we get a, which was the value below the radical sign, our radicand. Addition and subtraction between radicals. To add or subtract radicals, they must have the same radicand and index. Square root of 3 plus 2 times the square root of 3. That 2 square root of 3 implies a multiplication. It is as if there was the multiplication sign between the 2 and the square root of 3. So we can read it as 2 times the square root of 3. This is a compact way to write a product. In front of the square root of 3, there is an implicit 1. Even if we don't write it, it's as if there is a 1 multiplied by the square root. So 1 times the square root of 3 is simply equivalent to the square root of 3. This implication simplifies mathematical expressions for us without altering its value. So the square root of 3 plus 2 times the square root of 3 is equal to 3 times the square root of 3. It's like adding an equal object plus 2 other equal objects, obtaining a total of 3 times the square root of 3. Now we have another example, the square root of 2 plus the square root of 3. In this case, the radicand, the number under the radical sign, is not the same. Before, we had 3 in both. In this case, we have two different numbers, 2 and 3. Different radicand, therefore we cannot add them up together. Multiplication between radicals. To multiply the radicals together. If the indices are the same, you can combine them under a single radical sign. Square root of 7 times the square root of 2. Since the root index is the same, we can multiply the two radicals together and write the result under the same radical sign. This property makes it easier for us to calculate. So since both the square root of 7 and the square root of 2 are both square roots, they both have indices 2. Even if we have not written them, these are implicitly radicals with index 2. So we can multiply them together and put them below the same radical sign. So we do the square root of 7 times 2, which equals to the square root of 14. Division between radicals. To divide radicals, divide the radicands. If the indices are the same, you can combine them under a single radical sign. So we have the square root of 8 divided by the square root of 2. Since the indices of both radicals are equal, they are both square roots, we can put everything under a single radical sign, and then calculate 8 over 2, which is equal to 4. The square root of 4 is equal to 2, because 2 raised to the power of 2, which is the index of the square root, gives us 4. Radical in fractions. The root radical symbol. The radical symbol in fractions can be represented using exponents. We have radical of the nth power of a, which we can rewrite as a to the power of 1 over n. So we have written our index as a fraction of 1 over n, where n is the index of our radical. The square root of 4 can be rewritten as 4 raised to the power of 1/2, which equals to 2. We have the cube root. So a root with index 3 of 8. So we have rewritten it as 8 raised to the power of 1/3, which equals to 2, because 2 raised to the power of 3 gives us 8. Product property. The product of two radicals is equal to the radical of the product of the radicands. Square root of a times the square root of b equals the square root of a times b. The square root of 3 times the square root of 2 equals the square root of 3 times 2, which equals to the square root of 6. Quotient property. The quotient of two radicals is equal to the radical of the quotient of the radicands. The square root of a divided by the square root of b equals to the square root of a over b. The square root of 10 divided by the square root of 2. Since both have the same index, which is 2, we can put them below the same radical sign. So we have the square root of 10 over 2, which equals to the square root of 5. Power property. The radical of a power is equal to the power of the radical. Here we have the square root of a raised to the power of n, and here we have in parentheses the square root of a all together raised to the nth power. Here we have the square root of 2 raised to the second power. So we have in parentheses the square root all together raised to the power of 2 and gives us 2. So it's like this exponent here and the radical sign cancel each other out. Why does multiplying a radical by itself yield the radicand? The square root of a number, a, so the square root of a, is defined as the number that 1 square gives a. When you multiply the square root of a by the square root of a, you are essentially reversing the operation of the square root. Squared and take the square root are inverse operations. The square root of a times the square root of a, which is in parentheses the square root of a all raised to the power of 2, equals to a. So this 2 and the square root cancel each other out. The square root is index 2, and here we have 2, so they cancel each other out. So the square root of a times the square root of a equals a. Square root of 3 times the square root of 3 equals, in parentheses, the square root of 3, all raised to the power of 2, which equals to 3. We said that the radical can also be expressed in the form of an exponent. The square root of 3 can be rewritten as 3 raised to 1/2. This writing is useful because it allows us to easily apply the rules of exponentiation to simplify calculations. So pretty much here we have the square root of 3, and we have rewritten the square root as 3 raised to the power of 1/2, and in parentheses, everything inside the parentheses is raised to the power of 2. So we apply the power property, which is this one here, which is in parentheses we have a raised to the power of m, and outside the parentheses we have the exponent n, and we multiply m by n, so we have a raised to the power of m times n. So here we have 3 raised to the power of 1/2, which is our square root, times 2, which is our external exponent. So we simplify the 2's together, so we simplify this 2 in the denominator with this 2 in the numerator. This is like a fraction, 2 divided by 1. Even if we don't write, it's like 2 divided by 1. So it's just 2. So this is like in the numerator, and this is in the denominator. So we simplify them, and we get 1. 1 over 1 times 1, which equals to 1. So 3 raised to the power of 1 equals to 3. And so this is why the square root of 3 times the square root of 3 equals to 3. So in general, this is why when you multiply the square root of a number times the square root of the same number, so the same radicand, you get the radicand without the square root. Simplifying radicals. Simplifying a radical means reducing it to its simplest form by extracting the perfect squares. So here we have the square root of a raised to the power of 2 times b, and we have rewritten it as a outside the square root, a times the square root of b. Here we have the square root of 50. 50 can be rewritten as 25 times 2. The 25 is equal to 5 to the second power. So we can write the square root of 50 as the square root of 5 to the second power times 2. Through the property of the roots, we can take the 5 out of the radical sign by eliminating the exponent 2. We then rewrite the square root of 50 as 5 times the square root of 2. So we just applied this rule here. So we add this 50. We have rewritten it as 25 times 2. We have rewritten the 25 as 5 to the second power, which is 25. And following this, we have written the 5 outside the square root without the exponent. Then we just wrote the square root of 2. So we have simplified this square root of 50 as 5 times the square root of 2. Properties of radicals. Here I show the properties of radicals. Radicals raised to a negative power. When a radical is raised to a negative power, it corresponds to the reciprocal of the radical raised to the positive power. So we have the square root of 2 in parentheses, all raised to negative 1. We have rewritten the square root as 2 raised to the 1/2 power, in parentheses, all raised to negative 1. And so we multiply 1/2 by negative 1, and we get 2 raised to the power of negative 1/2. So 2 raised to the power of negative 1/2 is 1 over 2 to the power of 1/2. 1/2 is our square root. So 1 over the square root of 2. So this square root of 2 in parentheses all raised to negative 1 equals to 1 over the square root of 2. So in conclusion, the square root of 2 in parentheses all raised to the power of negative 1 is equal to 1 divided by the square root of 2. Percentages. Percentages are a way of expressing a number as a fraction of 100. They are often used to describe proportions, comparisons, and variations. This reads 50%. In blue, the number 50, which is also called the value, and in red, the percent sign. This is a circle divided in two with 1/2 color. 50% can be represented as half of the total, in this case, half the circle. It can also be represented as a fraction, as 1/2, or half of the circle. Or it can be indicated as 0.5 out of 1. One represents the entire circle. In fractions, 100 parts out of 100 indicate the entire circle. By simplifying the fraction 100 out of 100 and dividing both the numerator and the denominator by 100, we get 1/1, which is 1, or the entire circle. As a percentage, this can also be represented as 100%, 100 parts out of 100. Percentage as a proportion. A percentage represents a part of a whole in proportion to 100. 40% means 40 parts out of 100. 40% means 40 over 100. Percentages, decimals, and fractions. Percentages, decimals, and fractions are different ways of expressing the same value. They all represent parts of a whole, just in different forms. Percentages as parts out of 100, decimals as base 10 numbers, and fractions as ratios between two numbers. These are all ways to express the same thing. This is a percentage, 50%. This is a decimal, 0.5. And this is a fraction, 1/2. This is the formula to find the percentage. A part over the total times 100. Here we apply the formula. We took 1/2, that equals to 0.5, and we multiply it by 100, and we get 50%. 1/2 is 0.5 times 100, 50%. Conversion to fractions. Percentages can be converted to fraction by putting the percentage over 100. 25% equals to 25 over 100, which equals to 1/4. So we simplify this fraction. We divide both 25 and 100 by 25, and we got 1 in the numerator and 4 in the denominator. So 25% is like 1/4. Conversion to decimals. Percentages can be converted to decimals by dividing by 100. 75% equals to 75 divided by 100, which equals to 0.75. Percentage of a number. To find the percentage of a number, multiply the number by the percentage, expressed as a decimal. 20% of 50 equals to 50 times 20 over 100, which equals to 10. So 20 over 100 is 0.2. So 50 times 0.2 equals to 10. Percentage increase or decrease. The percentage increase or decrease is found by comparing the difference between two values to the original value, and then multiplying by 100. Product price $100. Increased by $20. The new price is $120. How much is the increase in percentage? Here we have a formula. The increase or decrease divided by the original price times 100 gives us the increase in percentage. So here we do the new value, which is 120, minus the original value, which was 100, and we divide it by the original price, which was 100, times 100 equals to the percentage increase. So 120, the new price after the increase, minus 100, the original price, divided by 100, the original price, times 100 equals to 20%. So our product has increased of the 20%. This 20% corresponds to our $20. So we increase the product price to the 20%. If we calculate 100 times 20%, we get 20. And 100 plus 20, 120, which is the new price. Here we have another example. Product price $80, decreases by $35. The new price is $45. How much is the decrease in percentage? So we do the original value minus the new value divided by the original value times 100, and we get our decrease in percentage. So we do 80, which is the original price, minus 45, which is the new price, all divided by 80, which is the original price, times 100, equals to 43.75%. So this is how much our product price has decreased. So 80 minus 35 is 45, and the product price has decreased of 43.75%, respect the original price. Finding the original value. To find the original value before a percentage change, divide the final value by 1 plus or minus percentage change as a decimal, where the plus sign is used for an increase and the minus sign for a decrease. Final price after 20% increase is $120. What was the original price? 120 divided by 1.2 equals to 100. 100 is our original price. Divided by 1.2 because 1 represents 100%, plus 0.2 representing the additional 20%. Percentage of a percentage. Finding a percentage of a percentage means multiplying the two percentages together. Find the 20% of 50%. 0.2, 0.20, or 0.2, which is the 20%, times 0.5, which is the 50%, equals to 0.10, which is the 10%. So the 20% of 50% is 10%. We could also have written it this way in the form of a fraction. So the 20% is 20 divided by 100, and 50% is 50 divided by 100. Then we simplify this. So we simplify the 20 with this 100, and we got 1 here and 5 here. And we simplify this 100 with this 50. So we got 1 here and 2 here. So 1/2 times 1/5 equals to 1/10. 1 divided by 10 is 0.1, which is the 10%. Absolute value. The absolute value of a number is its distance from 0 on the number line. It is always non-negative. Notation: an X enclosed between two vertical bars. These two vertical bars, enclosing the number, indicate the absolute value. The absolute value of -3 equals 3, because the distance between -3 and 0 on the number line is 3. In fact, -3 plus 3 equals 0. The absolute value of 5 equals 5, because the distance between 5 and 0 on the number line is 5. In fact, 5 minus 5 equals 0. Percentage error. Percentage error measures the difference between an estimated or measured value and a true value, expressed as a percentage of the true value. If you estimate that something weighs 50 grams, but in reality it weighs 45 grams, what is the percentage error? So here we have 50 minus 45. These vertical lines denote the absolute value. The absolute value of a number represents its distance from 0, regardless of the sign. In other words, if the result of an operation is negative, the absolute value converts it into a positive number, and if it's positive, it remains unchanged. So 50 minus 45 is 5, divided by 45 times 100 equals to 11.11%. Compound percentages. Compound percentages occur when multiple percentage changes are applied one after the other, cumulatively affecting the final value. If an initial investment of $100 grows by 10% in the first year, then another 20% in the second year, what is the final value of the investment? 100 times 1.1 times 1.2 equals 132. So in the first year, we have 100 plus 100 times 0.1. 0.1 is the 10%. So 100 times the 10% is 10. So 100 plus 10 equals to 110 after the first year. In the second year, we don't have 100 anymore. We have 110. So we do 20% of 110. So we do 20% of 110. So 110 plus, in parentheses, 110 times 0.2, which is the 20%, we get 132 after the second year. So 100 times 1.1, 110, 110 times 1.2, 132. Here we have another example. The original price of a product is $100. The first discount is 20%. The second discount is 10%. So we do 100, which is the price, minus 100 times 0.2, which is the 20%. 100 times 20% is 20. So 100 minus 20 is 80. Then we apply the second discount. So 80 minus 80 times 0.1, which is the 10%. The 10% of 80 is 8. So 80 minus 8 equals to 72. So after the 2 discounts, the new price of the product is 72. Applying two separate discounts is not the same as applying the sum of the discounts. So here on the left we have the same operation that we've done before. I just written it in a more compact way. So we have 100 minus 100 times 0.2, which is the 20%. So 100 minus the 20% of 100, which is 20. So 100 minus 20 is 80. 80 times the 0.1 is, so the 10% of 80 is 8. So 80 minus 8 equals to 72, which is what we calculated before. While here on the right, we have the sum of the discount, so 20% plus 10%. So the 30% of 100 is 30. So 100 minus 30 is 70. So here we are. 100 minus 100 times 30%. On the left, we have applied one discount and then we applied the second discount. On the right, we applied the sum of the discounts. So on the left, we applied 20%, then 10%. On the right, we applied the 30%. And as we can see, the results are different. 72 is not equal to 70. So at the end, applying two separate discounts is not the same as applying the sum of the discounts. 72, which is the separate discounts, is not equal to 70, which was the sum of the discounts. Ratios. A ratio compares two quantities by division, showing how much of one quantity there is relative to the other. It can be expressed in three ways: as a fraction, a over b, with a column, a colon b, which is read a to b, or by using the word to, a to b. These are all ways to express a ratio. Writing a colon b or writing a over b is the same thing, and both ways are read as a to b. The first number is called antecedent and the second is called consequent. Example: a basket with 4 apples and 2 oranges. What is the ratio between the two? Here we have our basket with 4 apples and 2 oranges. We wrote 4 to 2. The ratio is 4 to 2. This ratio can be simplified further by dividing both 4 and 2 by their greatest common divisor, which is 2. 4 divided by 2 is 2, and 2 divided by 2 is 1. So 2 to 1. There are 2 apples for each orange. Alternatively, if you wanted the ratio of oranges to apples, it would be the opposite, 1 to 2. There is 1 orange for every 2 apples. If we, for example, had 5 oranges and we would like to keep this ratio, we would consequently have 10 apples. Proportions. Proportions are statements that two ratios are equal, comparing two quantities by division. Example: one recipe calls for 3 cups of flour for every 2 cups of sugar. You want to make a smaller portion using 1 cup of sugar. How many cups of flour are needed for 1 single cup of sugar? Here on the left, we have 2 cups of sugar and on the right, we have 3 cups of flour. We want to make a smaller portion using a single cup of sugar. So here on the left, I put a cup of sugar, and on the right, I indicated with a question mark the number of cups of flour we will need that we still don't know and need to find out. On the left, I have the proportion of the original recipe that called for 3 cups of flour and 2 cups of sugar. On the right, I have the proportion for the recipe that uses a single cup of sugar. Here we have written 2 over 3 equal to 1 over x. We want to find out the value of that x. The x represents the number of cups of flour needed for a single cup of sugar. Cross multiplication. Cross multiplication is a method used to solve proportions, multiplying the numerator of one ratio by the denominator of the other and setting the products equal. So we want to multiply A times D and B times C. So what we need to do to find out the number of cups of flour is cross multiplication. Multiply 2 and x together and 1 and 3 together. Before we do that, we can rewrite the proportion like this. Note that instead of the equal sign, we can also use a double column, although this notation is less used. What we do is multiply the means and extremes together. The extremes, as the word implies, are at the ends of the proportion, while the means are those closest to the equal sign. So the extremes are 2 and x, and the means are 3 and 1. So let's multiply the extremes and the means together. 2 times x and 1 times 3. We got 2x equals 3. We need to isolate x by eliminating the coefficient 2 that multiplies it. Remember, even if the multiplication sign isn't shown, the term 2x means that 2 is multiplied by x. We need to remove the 2 to find out the value of x. To do this, we need to divide both sides of the equation by 2. This is an equation, which means that the values on one side must correspond to those on the other. If we do an operation on one side, we must also do it on the other to maintain the equality of the equation. We divided both 2x and 3 by 2. The two 2's, these 2's, are simplified, leaving only x, while here we have 3 over 2. So x is equal to 3 over 2. By dividing 3 and 2, we get 1.5. Thus, the value of x is 1.5. So we will need 1.5 cups of flour if we want to use a single cup of sugar. On the left, the original proportion, and on the right, the proportion that uses a single cup of sugar. So if we use 1 cup of sugar, we're going to need 1/2 cups of flour. Inversion property. If two ratios are equal, their reciprocals are also equal. This property is traditionally known as invertendo property. This property is also called the invertendo property, which is the original Latin name. I have translated it into English as the inversion property, but keep in mind that in textbooks you'll find it as invertendo property. So what we have is these two proportions. We took the reciprocal, which means we swap the positions of the terms in each ratio. In other words, the original proportion A is to B as C is to D becomes B is to A as D is to C. Here we just rewrote it as a fraction. For the reciprocal of a fraction, we simply flip the values of the numerator and the denominator. So we have 2 over 3 equals to 4 over 6. So here we just flip the 2 and 3, so we got 3 over 2, and here we flip the 4 and the 6, so we got 6 over 4. Alternation property. The alternation or alternando property of the means or extremes in a proportion is a property that states if you have a true proportion A over B equals C over D, you can swap the means or extremes to create another true proportion. This property is often referred to as switching or inversion of means or switching or inversion of extremes. So here we have a proportion where the means B and C, which are the numbers closest to the equal sign, are swapped. This gives us the new proportion. A is to C as B is to D. Likewise, when we swap the extremes, A and D, we obtain D is to B as C is to A. So we have essentially swapped the positions of the means and of the extremes. So this is the original. Here we swap C and B, which are the means. And here we swap D and A, which are the extremes. Two is to 3 as 4 is to 6. And here we inverted 4 and 3. So we did the switching of the means. So 2 is to 4 as 3 is to 6. While here we switch the extremes. 6 is to 3 as 4 is to 2. Here I just rewrote it as a fraction. This alternation demonstrates that by interchanging these parts, the proportion remains valid. We swap this denominator with this numerator, while here we swap 6 and 2. Composition property. The composition property, or componendo property, states that if two ratios are equal, you can add the numerator to the denominator in both ratios and the resulting ratios will still be equal. So here we have A plus B is to B as C plus D is to C. So we just added B to A, and here we added C to D. And here we have A plus B is to A as C plus D is to D. So here we have 2 is to 3 as 4 is to 6. And we have 2 plus 3 is to 3 as 4 plus 6 is to 6. So we added the 3 to the 2, and here we add the 6 to the 4. So we added the denominator Here is not written as a fraction, but it's the same. After doing these sums, we got 5:3 as 10:6. So both ratios after the additions remain the same. Decomposition property. The decomposition property, or dividendo property, states that if two ratios are equal, you can subtract the denominator from the numerator in both ratios, and the resulting ratios will still be equal. If A is greater than B, A minus B is to B as C minus D is to C. A minus B is to A as C minus D is to D. Here we have 5:3 as 10:6. We subtracted the denominator, the consequent, from the numerator, the antecedent, 5 minus 3 is to 3 as 10 minus 6 is to 6. What we got is the proportion we originally started with in the composition property. So 2:3 as 4:6. And here I just rewritten it as a fraction. Proportions properties. This is a summary of the properties of the proportions. Set. A set is a collection of distinct objects, considered as an entity. Objects in a set are called elements or members of the set. To define a set name, a single uppercase letter, example, A, B, S, etc. Elements of the set. They can be numbers, letters, objects, or even other sets. Separation of elements. Elements are separated by commas. Rules for defining elements. Rules can be used to define the elements of the set. Closing the set. The whole set is enclosed in curly brackets. Example of a set, n equals 1, 2, 3, and 4. So this is a set with the name n, which elements are 1, 2, 3, and 4. Here we have another example of a set. This is a set identified by the capital letter V. The elements in the set are listed in curly braces, and each element is unique with no repetitions. In this case, the set represents the vowels A, E, I, O, U. Venn diagram. In addition to textual representation, sets can be represented graphically using a Venn diagram, where a set is depicted as a circle and the elements of the set are placed within the circle. Each circle represents a different set, and overlapping circles can show relationship between sets, such as intersections or unions. This is the graphical representation of the set of vowels. So we have a circle inside which all the elements of our set are present. Sets of numbers. Number sets are collections of numbers that share common properties and are grouped into categories based on these properties. Examples include natural numbers, defined with this n in a blackboard bold style. In this way, integers, z, rational numbers, Q, real numbers R, and complex numbers C. Therefore, all the numbers are contained in these sets. Set of natural numbers. The set of natural numbers includes all positive integers starting from 1 and continuing to infinity. It is represented by the symbol n. N equals 1, 2, 3, 4, and so on to infinity, where the ellipses indicate that the sequence of numbers continues in a pattern that the set follows. So, the set of natural numbers is from 1 to infinity, so here we're just representing 1, 2, 3, and 4, but after 4 there are infinite numbers. This is a graphical representation of the set of natural numbers. Here we see only a few members, because it is not possible to show them all, since the set includes all positive numbers from 1 to infinity. Member of. The member of symbol is used to indicate that an element belongs to a set, is a member of a set. The number 3 is a member of the set of natural numbers. If we remember, all positive numbers from 1 to infinity are part of the set of natural numbers. Not member of. The not member of symbol is used to indicate that an element does not belong, is not a member of, a set. -1 is not a member of the set of natural numbers. -1 does not belong because it is a negative number, while only positive numbers from 1 to infinity belong to the set of natural numbers. Set of whole numbers. The set of whole numbers, or non-negative integers, consists of all integers greater than or equal to 0. It is represented by the symbol W, or sometimes by n sub 0, or z greater or equal than 0. W equals 0, 1, 2, 3, 4, and so on. Set of integers. The set of integers includes all positive and negative integers, as well as 0. It is represented by the symbol z. Z equals -3, -2, -1, 0, 1, 2, 3. And the ellipses before the negative numbers and after the positive numbers means that the set continues both toward negative infinity and positive infinity. Set of rational numbers. The set of rational numbers includes all numbers that can be expressed as fractions of two integers, where the denominator is not 0. It is represented by the symbol q. Q equals 1/2, 3/4, -5/6, 0.25, -3.8, and so on. Set of irrational numbers. The set of irrational numbers includes all numbers that cannot be expressed as a fraction of two integers. It is represented by the symbol q prime, or r minus q, or sometimes I. R minus q equals the square root of 2 pi e negative square root of 5, and so on. Set of real numbers. The set of real numbers includes all rational and irrational numbers. It is represented by the symbol r. R equals the square root of 2 pi -1, 0.5, 3, and so on. Set of complex numbers. The set of complex numbers, denoted by C, includes all complex numbers which are numbers of the form a plus bi, where a and b are real numbers, and I is the imaginary unit with I squared equals negative 1. C equals 3 plus 4i, negative 2i, 7 minus 9i, and etc. I is the imaginary unit, where I equals to square root of negative 1, and I squared equals to negative 1, which is essential for calculating the square roots of negative numbers. Sets of numbers. This is a Venn diagram representing the sets of numbers. Note the set of positive integers and irrational numbers are not explicitly shown, but they are still included in the diagram. The natural numbers set is a subset of the integer set, which includes all positive, negative, and zero numbers. The set of rational numbers, on the other hand, also includes numbers that can be expressed as fractions of two integers. The set of real numbers includes all rational and irrational numbers. Finally, the set of complex numbers represents all the numbers of the form a plus bi, where I is the imaginary unit with I squared equals negative 1. Subset. The symbol subset means is a subset of, indicates that all elements of one set are also elements of another set. The set of natural numbers is a subset of the set of positive integers. The set of natural numbers is a subset of the set of integers. This, in turn, is a subset of the rational numbers, which is included in the set of real numbers. Finally, the set of real numbers is contained in the set of complex numbers. Unit of measurement. Units of measurement are standard quantities used to express and compare physical properties such as length, mass, time, and volume. These units allow us to measure and communicate the size, quantity, or degree of something in a consistent and understandable way. CGS system. The CGS, centimeter, gram, second system, is a metric system of units introduced in the early 19th century by Carl Friedrich Gauss. It uses centimeters for length, grams for mass, and seconds for time as the base units. The CGS system was widely used in scientific fields before being largely replaced by the MKS system, which then evolved into the modern International System of Units, SI. The CGS system is a historical precursor to the SI, which laid the foundation for the development of a more universally standardized measurement system. MKS system. The MKS, meter kilogram second system, is a metric system of units that uses the meter for length, the kilogram for mass, and the second for time as the base units. It was introduced at the end of the 19th century, gaining wide use as a practical and standardized measurement system, particularly in engineering and science. The MKS system served as a direct precursor to the International System of Units, SI, which expanded the system to include additional units and refine it for universal use. Imperial system. The imperial system is a measurement system developed and used in the British Empire since the 19th century and still used today in the United States. It includes units such as the inch for length, pound for weight, and gallon for volume. This system evolved from ancient English units and was officially defined in 1824 with the British Weights and Measures Act. International System of Units (SI). The International System of Units (SI) is a globally accepted and standardized system of measurement used for physical quantities such as length, mass, time, and temperature. It is the modern form of the metric system and provides a consistent framework for measurements in different fields of science, industry, and daily life. International System of Units Brief History. The International System of Units (SI) was established in 1960 to create a universal standard for measurements, ensuring consistency and accuracy in science, industry, and commerce globally. Prior to the SI, there were various systems of measurement, including the metric system in Europe and the imperial system in England, leading to inconsistencies and difficulties in international trade and scientific collaboration. Base units of the SI. The SI base units are the fundamental units of measurement of the International System of Units (SI), from which all other units are derived. Each base unit corresponds to a specific physical quantity, such as length, mass, time, or temperature. Base units of the SI. These are the basic units of the international systems. So here we have quantity, the unit, and the symbol of the unit. So for length, we have the meter with the symbol m. For mass, we have the kilogram with the symbol kg. For time, the unit of reference is the second with the symbol s. For electric current, we have the ampere with the uppercase A. Temperature is Kelvin with the uppercase K without any degree symbol, just the K. For amount of substance is the mole with the MOL symbol, with the mole symbol. For luminous intensity is the candela, which is CD. Meter, M, unit of length. The meter, M, is the SI base unit of length. Length is the measure of the distance between 2 points. Here we have 2 points in space called A and B, and we've aligned their distance. Here, the meter is used to represent distance between 2 points, just like between A and B. Here we have a 20 centimeter ruler. Beside it are two 1 meter rods, each exactly 1 meter long, illustrating the base unit of length in the International System of Units. The centimeter is ideal for precise, small-scale measurements, while the meter provides a practical reference for everyday distances and heights. Kilogram, kg, unit of mass. The kilogram, kg, is the SI base unit of mass. Mass is the measure of the amount of matter in an object. Here we have a weight marked in kilograms. Such standardized weights are used to verify and adjust scales, ensuring accurate measurement of mass in both laboratory and everyday settings. Second, S, unit of time. The second, S, is the SI base unit of time. Time is the continuous progression of events from the past to the present to the future. This is an hourglass. This hourglass symbolizes the passing of time. As the fine sand flows from the upper bulb to the lower one, it reminds us how moments slip away and underscores the value of each grain in marking our days. Kelvin, K, temperature unit. The Kelvin, K, is the SI base unit of temperature. Temperature is a measure of the thermal energy of a substance. This here is William Thomson First Baron Kelvin, a British physicist and mathematician, known for his contributions to thermodynamics and for developing the absolute temperature scale that bears his name, the Kelvin scale. Ampere, unit of electric current. The ampere, A, uppercase A, is the SI base unit of electrical current. Electric current is the flow of electric charge through a conductor. Here we have an amperometer, which calculates the electrical current. And here we have André-Marie Ampère, a French physicist and mathematician considered one of the founders of electrodynamics. The unit of measurement of electric current, the ampere, is named after him for his important contributions to the study of electricity and magnetism. Mole, mole, unit of amount of substance. The mole, MOL, is the SI base unit of the amount of substance. The amount of substance refers to the number of particles, atoms, molecules, etc. in a given sample. On the right, we see Amedeo Avogadro, an Italian physicist and chemist known for the Avogadro's number, which represents the number of particles in a mole. However, the unit of mole as we know it today was formally introduced by Friedrich Wilhelm Ostwald, a German chemist and Nobel Prize for Chemistry in 1909 for his work on catalysis and chemical equilibrium. Candela, CD, unit of luminous intensity. The candela, CD, is the SI base unit of luminous intensity. Luminous intensity is the measure of the perceived power of light emitted by a source in a particular direction. Here it is represented a candle for this unit. The unit is called candela since the term derives directly from the Latin candela, which means candlelight. SI-derived units. SI-derived units are units of measurement that are derived from SI-based units through multiplication, division, or other mathematical operations. They represent quantities such as area, volume, velocity, and force. These are all the derived units. Don't worry, because it is not necessary to know them all. In fact, we don't need them at all for our arithmetic course. This will be useful for more advanced mathematics courses. SI prefixes. SI prefixes are used to represent multiples or fractions of SI units. They make it easier to express very large or very small quantities by scaling base units. These are the SI prefixes. Here we have 10 raised to the n power. Here we have the prefix. Here we have the symbol. Here we have the name. Here we have the decimal equivalent. In the SI prefix chart, 10 raised to the power of 0 corresponds to the unit itself, 1. Prefixes above 10 raised to the power of 0 represent multiples greater than 1. 10 raised to the power of 1, 10 raised to the power of 2, and so on. While prefixes below 10 raised to the power of 0 denote submultiples less than 1. 10 raised to the power of negative 1, 10 raised to the power of negative 2, and so on. This systematic progression makes it easy to scale any quantity up or down by powers of 10. By moving one step up or down the table, you simply multiply or divide by 10. This consistency is what gives the SI system its clarity and universal applicability across science and engineering. The names of the values such as billion, trillion, quadrillion, quintillion, and so on varies according to whether the long scale or the short scale is used. The table above employs the short scale, in which each successive term represents a value 1000 times larger than the previous. Long and short scales. Long scale. In the long scale, each new term for a number above a million is 1,000,000 times the previous one. For example, a billion is a million million, a trillion is a million billion, and so on. Short scale. In a short scale, each new term for a number above a million is 1000 times the previous one. For example, a billion is 1000 million, a trillion is 1000 billion, and so on. So here we have million in the long scale, and in the short scale is the same. In the long scale we have milliard, while in the short scale we have billion. In the long scale we have billion, while in the short scale we have trillion. Here we have billiard, and here quadrillion, trillion, quintillion, trilliard, sextillion, quadrillion, septillion, quadrilliard, octillion. So we need to be careful whether we are talking about long scale or short scale. Because for example, a billion in the long scale is not the same value as a billion in the short scale. And a trillion in the long scale is not the same as a trillion in the short scale. The main difference between the short and long scale systems lies in the value of terms like billion, trillion, etc. In the short scale, a billion equals 1000 million. In the long scale, a billion equals a million million. As a result, terms like trillion, quadrillion, etc. have different values in the two systems. On this map, countries shown in green use the long scale, where a billion denotes a million million. You'll find the long scale throughout continental Western Europe, Mexico, parts of South America, several African nations, and Iran. In blue, we see the short scale, where a billion equals 1,000 million. This is predominant in the United States, the United Kingdom, Australia, New Zealand, Brazil, several African nations, and many English-speaking Latin American countries. Russia and some other former Soviet states, several African nations, a few countries in the Middle East, a few countries in Southeast Asia, employ the short-scale terminology, but call 1,000 million a milliard instead of a billion. Canada and South Africa are officially bilingual here. Both scales appear in different contexts. Finally, a handful of countries, China, India, Pakistan, Bangladesh, Japan, Korea, Thailand, Vietnam, Greece, Mongolia, and others, use their own traditional large number naming conventions, rather than strictly long or short scale terms. Conversions. Here we see the scale of the units of measurement of weight, which starts from the kilogram, the largest unit, up to the milligram, the smallest unit. The arrows indicate the direction of unit conversion, showing whether to multiply or divide when going from larger to smaller units, and vice versa. For example, to convert kilograms to grams, we need to multiply by 10 as many times as there are positions between the two units. On the contrary, to go from grams to kilograms, we have to divide by 10 as many times as there are positions up to the kilogram. In this example, we want to convert 24 grams to kilograms. Here the question mark indicates that we do not yet know the resulting value. Let's start from the unit of gram, and we take a step to the left to reach the decagram. To do this, we divide our 24 grams by 10, which is 2.4 decagrams. Then we take another step to the left towards the hectogram. So we divide our 2.4 decagram by 10 to get 0.24 hectograms. Finally, we take a last step to the left to get to kilograms. Dividing our 0.24 hectograms by 10, we get 0.024 kilograms. In total, we took 3 steps to the left to convert grams to kilograms. This means that we divided our 24 grams by 10 3 times in a row, which is the equivalent of dividing 24 by 1000. So 24 grams is 0.024 kilograms. Here we still have 24 grams, but this time we want to convert it to milligrams. Since we are converting from the gram to a smaller unit, the milligram, we have to multiply instead of dividing. So let's take a step to the right, multiplying 24 grams by 10 and getting 240 decigrams. Then one more step, multiplying by 10 again to get 2400 centigrams. Finally, multiplying by 10 one last time, we get 24,000 milligrams, which corresponds to our 24 grams converted to milligrams. In conclusion, to convert from grams to milligrams, we multiply by 10 3 consecutive times, equivalent to multiplying directly by 1000. So 24 grams is 24,000 milligrams. In this example, we want to convert 2 kilograms into grams. To go from kilogram to gram, we need to take 3 steps to the right on a unit scale by multiplying by 10 at each step. This is equivalent to multiplying directly by 1000, obtaining 2000 grams. So in total, we multiply 2 by 1000 to get 2000 grams. 2 kilograms corresponds to 2000 grams. Finally, in this last example, we have 2000 milligrams, and we want to convert them into grams. To convert milligrams to grams, we need to take 3 steps to the left on the unit scale, dividing by 10 at each step. This is equivalent to dividing directly by 1000, obtaining the value in grams. So 2000 milligrams is 2 grams. Celsius scale. The Celsius scale is a temperature scale where 0 degrees Celsius is the freezing point of water and 100 degrees Celsius is the boiling point at standard atmospheric pressure. This one in the painting is Anders Celsius, the Swedish scientist to whom we owe the Celsius scale. Standard atmospheric pressure, 1 atmosphere, is the average air pressure at sea level, defined as 101,325 pascals. Fahrenheit scale. The Fahrenheit scale is a temperature scale where 32 degrees Fahrenheit is the freezing point of water and 212 degrees Fahrenheit is the boiling point at standard atmospheric pressure. Here we see Daniel Gabriel Fahrenheit, a Polish German physicist and engineer. He invented the mercury thermometer and developed the Fahrenheit scale. The scale is still mainly used in the United States and in a few little countries. Rankine scale. The Rankine scale is an absolute temperature scale using degrees Fahrenheit, developed by Scottish engineer William John McQuern Rankine. Like the Kelvin scale, it starts at the absolute zero, but its increments are equal to degrees Fahrenheit. This is William John McQuern Rankine. A Scottish engineer and physicist, is known for his pioneering work in thermodynamics and for introducing the Rankine scale. Réaumur scale. The Réaumur scale was developed by the French scientist René-Antoine Verschold de Réaumur in the 18th century. It defines 0 Ray as the freezing point of water and 80 Ray as the boiling point. It was used in some regions of Europe, but fell into disuse with the adoption of more practical scales such as Celsius. Here we see René-Antoine Verschold de Réaumur, a French scientist known for the Réaumur scale. Although it is little used today, the scale was important in the 18th and 19th centuries. Temperature conversions. These are the formulas for converting temperatures between different scales. The Rankine and Réaumur scales, now in disuse, have been omitted from the scheme, but the three most used scales are present. Celsius, adopted all over the world, Kelvin, the basic unit of temperature in the International System, SI, and Fahrenheit, which is mainly used in the United States and a few other countries. So here we have the formula to convert from Celsius to Fahrenheit. So we need to do 9 over 5 times the temperature in Celsius plus 32. While to convert from Celsius to Kelvin, we need to, this is the degrees in Celsius plus 273.15, which is the absolute temperature in Kelvin. To convert a temperature from Kelvin to Celsius, subtract 273.15 from the Kelvin value. This shows how closely the two scales are related, so you can see these formulas are inverse of each other. So here in Celsius to Kelvin we added, from Kelvin to Celsius we subtracted. To convert from Kelvin to Fahrenheit, we do 9 over 5 times Kelvin minus 273.15 plus 32. Absolute zero is the lowest possible temperature, 0 Kelvin, which is negative 273 26.15 degrees Celsius, at which particles have minimal vibrational motion. To convert from Fahrenheit to Celsius, we do 5/9 times the degrees Fahrenheit, so our temperature in Fahrenheit minus 32. To convert from Fahrenheit to Kelvin, we do 5/9 times F minus 32 plus 273.15. Note, Kelvin temperatures are written without the degree symbol, whereas Celsius and Fahrenheit have it. So here we have a few examples. Here we want to convert 27 degrees Celsius in Fahrenheit, and same for Kelvin. While for Kelvin we want to convert 300 Kelvin into Celsius and then into Fahrenheit. While for Fahrenheit we want to convert our 87 degrees Fahrenheit into Celsius and then into Kelvin. So we put the 27, which was our degrees Celsius, here, and we did this multiplication plus 32, and we got 80.6, which is our temperature in Fahrenheit. So 27 degrees Celsius corresponds to 80.6 degrees Fahrenheit. And here we did 27 plus 273 plus 15, which is 300.15, which is our temperature in Kelvin. So 27 degrees Celsius corresponds to 300.15 Kelvin. Here we did 300, which was our temperature in Kelvin, minus 273.15, which is 26.85 degrees Celsius. So 300 Kelvin corresponds to 26.85 degrees Celsius. Then here we have 300 Kelvin, and we did these operations, and we got 80.33 degrees Fahrenheit. So 300 Kelvin corresponds to 80.33 degrees Fahrenheit. Then here we have 86 degrees Fahrenheit, and we did this operation, and we got 30 degrees Celsius. So 86 degrees Fahrenheit corresponds to 30 degrees Celsius. While here we plug in our 86 here, we did this operation here, and we got 303.15. So 86 degrees Fahrenheit corresponds to 303.15 Kelvin. The liter. A liter is a unit of volume in the metric system used to measure the amount of space occupied by a substance, usually a liquid. Volume refers to the three-dimensional space that an object or substance fills. The liter symbol is lowercase l, but sometimes uppercase L is also accepted as an alternative to avoid confusing lowercase l with the number 1. This is a container with a scale in milliliters. Imperial units and conversions. The imperial system is a system of measurement used primarily in the United Kingdom and formerly in the British Empire. It includes units such as inches, feet, miles, and pounds. Conversions between the imperial system and the SI system are necessary for standardization in science and international trade. Note that while these units are similar, there are differences between the American and British imperial systems. Note that there are many imperial units, but we will not cover them all, just a few. Approximately equal to. The symbol double tilde means approximately equal to. It indicates a numerical approximation. Pi is approximately equal to 3.1416. The double tilde symbol is read approximately equal to and is used to indicate a rounded value. Pi is not exactly 3.1416 because it has infinite decimals, so the equality is approximate, not exact. Therefore, hence, the symbol of the three dots forming an upward pointing triangle means therefore or hence. It is used to indicate a logical conclusion that follows from previous statement. If A equals B and B equals C, therefore A equals C. Hence, A equals C. So, A equals C. Implies the arrow, long double line arrow, or the arrow of logical implication, or the short single line arrow, the material implication arrow, means implies logic. If P then Q, x greater than 2 implies x greater than 1. There are two kinds of implications. The long double line arrow corresponds to the logical implication, while the short single line arrow corresponds to the material implication. Length. Length is a measure of the distance between 2 points. Inch. An inch is a unit of length in the imperial system. It is commonly used for smaller measurements, such as the size of a smartphone screen or the height of a person. We can both use the IN symbol for inch or the double prime symbol. Conversions. 1 inch is approximately 2.54 centimeters, while 1 centimeter is approximately 0.3937 inches. Example: a smartphone screen is about 6 inches. How many centimeters is that? So we said 1 inch is approximately 2.54 centimeters, as 6 times 2.54 is approximately 15.24 centimeters. Feet. A foot, plural fit, is a unit of length in the imperial system, often used to measure heights or short distances. We can use the symbol FT, or we can use the single quote mark. Conversions. 1 foot is approximately 0.3048 meters, while 1 meter is approximately 3.281 feet. Example: a room's ceiling is about 10 feet high. How many meters is that? So 1 foot is approximately 0.3048 meters, as 10 times 0.3048 is approximately 3.048 meters. Yard, YD. A yard is a unit of length in the imperial system, commonly used in the United States and the United Kingdom. Conversions. 1 yard is 0.9144 meters. 1 meter is 1.094 yards. Example: a football field is about 100 yards. How much is it in meters? 1 yard is around 0.9144 meters. As 100 times 0.9144 is around 91.44 meters. Mile, MI. A mile is a unit of length used primarily in the United States and the United Kingdom, amounting to 1.60 kilometers. Conversions. 1 mile is approximately 1.60 kilometers. 1 kilometer is approximately 0.62 miles. Example. A car travels 3 miles on the highway. How many kilometers is that? If 1 mile is approximately 1.60 kilometers, hence 3 times 1.60 is approximately 4.8 kilometers. Volume. Volume is a measure of the amount of space an object occupies. Fluid ounce. A fluid ounce is a unit of volume used in the US imperial and customary systems, primarily to measure liquids. Conversions. 1 fluid ounce is approximately 29.57 milliliters, while 1 milliliter is approximately 0.03 fluid ounces. Example. A bottle of juice contains 16 fluid ounces. How many milliliters is that? If 1 fluid ounce is approximately 29.57 milliliters, 16 times 29.57 is approximately 473.176 milliliters. Pint, PT. A pint is a unit of volume in the US imperial and customary systems, equal to 1/2 quart or 1/8 of a gallon. Conversions. 1 pint is approximately 568.26 milliliters. 1 milliliter is around 0.002 pints. Example. A glass of beer is 1 pint. How many milliliters is that? 1 pint is approximately 568.26 milliliters. So 1 times 568.26 is approximately 568.26 milliliters. Quart, QT. A quart is a unit of volume used in the US imperial and customary system, equal to 1/3 of a gallon. Conversions. 1 quart is around 0.94 liters. 1 liter is around 1.05 quarts. Example. A carton of milk contains 2 quarts. How many liters is that? 1 quart is around 0.94 liters. Therefore, 2 times 0.94 is approximately 1.89 liters. Gallon. A gallon is a unit of volume used in the imperial system and the US customary system to measure liquids. This is a typical gallon container in the US, commonly used for everyday liquids, like milk and water. Conversions. 1 gallon, this double tilde symbol means approximately. So 1 gallon is approximately 3.785 liters. So it's not really a precise value, but it's approximately this value. While 1 liter is approximately 0.264 gallons. Example, we have 15 gallons of gasoline. How many liters is that? So we said 1 gallon is approximately 3.785 liters. So 15 times 3.785 is approximately 56.73 liters. Weight. Weight is a measure of the force of gravity acting on an object. Ounce. An ounce, OZ, is a unit of weight used in the imperial system. It is commonly used to measure small amounts of mass, such as food or stamps. Conversions. 1 ounce is approximately 28.35 grams. 1 gram is approximately 0.0353 ounces. Example. A gold bar weighs about 38 ounces. How many grams is that? 1 ounce is approximately 28.35 grams. Hence, 38 times 28.35 is approximately 1077.3 grams. Pound. A pound, lb, is a unit of mass used in the imperial system and the US customary system. lb is derived from the Latin libra. Conversions. 1 pound is around 0.454 kilograms. 1 kilogram is around 2.205 pounds. Example. We want to know how much the weight of 70 kilograms is in pounds. We said 1 kilogram is approximately 2.205 pounds, and this 3-dot symbol means therefore. So therefore, 70 times 2.205 pounds is approximately 154.35 pounds. Short ton, TN. A ton is a unit of weight in the US and UK systems with different values. Short ton, US, 2,000 pounds, 907 kilograms. Long ton, UK, 2,240 pounds, 1,016 kilograms. Conversions. 1 short ton is around 907.18 kilograms. 1 kilogram is approximately 0.001 short ton. Example. A truck carries 5 short tons of cargo. How many kilograms is that? 1 short ton is around 907.18 kilograms. This implies 5 times 907.18 is approximately 4,535.92 kilograms, which is 4.5 metric tons. Long ton, LT, WT. Conversions. 1 long ton is approximately 1,016.046 kilograms. 1 kilogram is around 0.00098 long ton. Example. A load weighs 2 long tons. How many kilograms is that? We had said that 1 long ton is around 1016.046 kilograms. Therefore, 2 times 1016.046 is around 2032.092 kilograms, which is 2 metric tons and a bit more. Ton, Tn, versus ton, T, single T. The metric ton, tonnen, with a single T, is a SI unit equal to 1000 kilograms, while the short ton, USA, is 907 kilograms, and the long ton, UK, is 1016 kilograms. So in the metric system and the SI units, we use the metric ton, which is 1000 kilograms. So when we have 1000 kilograms, we can say we have 1 metric ton. Here's an overview of the main imperial system units covered, organized by category: length, volume, and weight, from the smallest on the left to the largest on the right. Division by zero. Dividing any number by zero is undefined in mathematics because it does not lead to a finite value or a meaningful number. N over 0, where n is a number. 5 over 0 equals undefined. If you have 5 apples and you want to divide them among 0 people, it is impossible to distribute them evenly since there is no group to distribute the apples to. Zero divided by a number. 0 divided by any non-zero number is always 0. 0 over n for n not equal to 0 equals 0. 0 over 7 equals 0. This is because if you have 0 items and you want to distribute them among a group, each party member will receive 0 items. Division by 1. Any number divided by 1 is the number itself. N over 1 equals n. 7 over 1 equals 7. It's like having 7 whole cakes not cut in pieces. This is because dividing a quantity into a single part leaves the original quantity unchanged. A number to the power of 0. Any non-zero number raised to the power of 0 is always 1. N raised to the power of 0 equals 1. 8 to the power of 0 equals 1. This follows the rules of exponentiation, where n raised to the power of 0 equals 1 for n not equal to 0. 0 to the power of 0. 0 raised to the power of 0 is an indeterminate form in mathematics, which means that it does not have a universally recognized value. However, in some contexts, it is referred to as 1 for convenience, while in others, it remains undefined. 0 raised to the power of 0 equals 1 or undefined. Number to the power of 1. Any number raised to the power of 1 is a number itself. N raised to the power of 1 equals n. 8 raised to the power of 1 equals 8. This is because raising a number to the power of 1 means multiplying the number by itself only once. This is the arithmetic formula cheat sheet, a printable summary of the entire course. If you'd like to get it, you can find it on Gumroad, link in the description and in the pinned comment. Thanks for watching and see you in the next video. If you'd like to download the full printable slides, the exercises, and the final cheat sheet, you can find everything on Gumroad. Link in the description and in the pinned comment. Thanks for watching and see you in the next video. Arithmetic Course Review. Welcome to the Arithmetic Course Review. In this video, we'll go through a concise recap of the entire arithmetic course. A quick walkthrough to refresh your memory of the key ideas. Before we begin, a short note. There are useful topics related to arithmetic that we haven't covered in this course. For example, an introduction to basic geometry and common shapes. That material will be offered in a separate, dedicated geometry course. Now, let's briefly review the main concepts from the course to help you spot any gaps and refresh what you've learned. Arithmetic. We began the course by explaining the etymology of the word arithmetic and giving a clear definition. Numbers. Next, we moved on to introduce numbers. These are the 10 digits we use to build every number. Brief history of numbers. After that, we gave you a quick overview of the history of numbers, from the Sumerians to the ancient Romans. You can see here the numerals used by each civilization. Then, we covered the Indo-Arabic numerals we use today and how they led to modern notation. This here is Al-Khwarizmi, while here we have Sir Isaac Newton, Descartes, and Leibniz. Numerical systems. Different bases change how place value works. Binary is base 2, octal is base 8, and decimal is base 10, and so on. At the end, we look at an old Sumerian counting method that used the finger phalanges, which are these segments of the finger. Numbers from 0 to a trillion. We also review numerical magnitudes from 0 up to 1 trillion, a large but finite range, of course, since there are infinitely many numbers overall. You can write these large numbers in different ways. without separators, with a space every 3 digits, or using a comma for clarity. Operations. The fundamental operations of arithmetic are addition, subtraction, multiplication, and division. Everything in basic arithmetic is built on these 4 operations. Times tables. Times tables allows us to remember the multiplications from 1 to 10 quickly. Properties. The properties of operations are rules that describe how the order and grouping of operands affect the result. Here is a summary table showing which properties apply to each operation. And here are the formulaic statements for each property. Negative numbers. Here we have negative numbers and some example operations with them. For multiplication and division with negative numbers, remember, same signs give a positive result. Different signs give a negative result. Factors and multiples. A factor divides a number exactly. That is, with remainder 0. A multiple is a product of that number. Use factors to find the greatest common divisor, GCD, and multiples to find the least common multiple, LCM. Even and odd. Even numbers are divisible by 2 with no remainder. Odd numbers are not. Prime and composite numbers. Prime numbers have exactly 2 divisors, 1 and themselves. Composite numbers have more than 2 divisors. Prime factorization is the basis for finding the greatest common divisor, GCD, the least common multiple, LCM, and for many mathematical proofs. Fractions. A fraction represents parts of a whole. the numerator, the number above the line, over the denominator, the number below the line. Here we have the types of fractions: proper, improper, and mixed. Equivalent fractions show the same value using different numbers. For example, all of these fractions here correspond to the value of 1/2. The greatest common divisor, GCD, is the largest factor two or more numbers share. The least common multiple, LCM, is the smallest multiple common to those numbers. To multiply fractions, multiply the numerators together and the denominators together. To divide, invert the second fraction. That is, take the reciprocal of the second fraction, and then multiply. Rationalization removes a radical from the denominator. Multiply a fraction by a form of 1 that places the radical in both numerator and denominator. Using the property of square roots, this eliminates the root from the denominator. Arithmetic mean and weighted average. Arithmetic mean, the sum of the values divided by the number of values. Weighted average. Multiply each value by its weight. Sum those products. Then divide by the total weight. Useful when some parts count more than others. Median. The median is the middle value in an ordered list. If there is an even number of elements, the median is the arithmetic mean of the two middle values. Powers. A power is repeated multiplication of the same number. The base is the number being multiplied, and the exponent tells how many times to multiply it. Here are some common mistakes people make when working with powers. This is a summary of the rules and properties of exponents. Order of operations. These are acronyms to remember the order of operations and the reminders for the sequence in which to perform mathematical operations. Logarithms. A logarithm is the exponent to which a fixed base must be raised to produce a given number. Here's a summary of the properties of logarithms. Decimals. This chart shows the decimal separator, the symbol placed between the integer and decimal parts, usually a dot or a comma, and how it's used in different countries. These are the 4 basic operations with decimals: addition, subtraction, align the decimal points, multiplication, multiply as if there were integers, then reinsert the decimal point, division, shift the decimals to eliminate fractional places, then divide. Repeating decimals. Repeating decimals are numbers whose decimal part repeats indefinitely. Notation for repeating decimals varies by country. The notation we use here is the vinculum, a bar placed over the repeating digits. Radicals. A radical is the inverse operation of exponentiation, represented by the radical sign. It indicates taking a root of a number or expression. Here's a summary of the properties of radicals. Percentages. Percent means per hundred. You can convert a percent to a fraction by writing it over 100 and simplifying, and convert between percent and decimal by dividing or multiplying by 100. Ratios and proportions. Ratios compare quantities. Proportions set two ratios equal. Cross multiplication is the standard method to find the unknown term in a proportion. Here's a summary of the properties of proportions. Sets. A set is a collection of distinct elements. You can define a set either by listing its elements between curly braces or by giving a rule that describes membership. Sets of numbers. These are the sets of numbers and the relations between them. Units of measurement and conversions. These are the base units of the International System of Units, SI. These are the SI prefixes. Prefixes scale units by powers of 10, making very large or very small values easier to read. long and short scales. The long scale and the short scale are two different naming systems for numbers larger than a million. This map shows which countries use the long scale, which use the short scale, and where alternative naming conventions are used. Conversions. To convert from one unit to another, multiply or divide depending on the direction of the conversion. For example, to convert grams to kilograms, that is, from a smaller unit to a larger one, divide by 1000. Equivalently, move the decimal point 3 places to the left. To convert from grams to milligrams, from a larger unit to a smaller one, multiply. In this case, multiply by 1000. Temperature scales. These are the formulas to convert between the three main temperature scales: Kelvin, Celsius, and Fahrenheit. This is a summary of the main imperial units, grouped by category: length, volume, and weight. Special cases of arithmetic. Here are some special cases of arithmetic. Division by zero is undefined. 0 divided by any non-zero number equals 0. Dividing by 1 leaves a number unchanged. For any non-zero n raised to the power of 0 equals 1. The expression 0 raised to the power of 0 is indeterminate in many contexts. In some specific contexts, it is defined as 1, so treat it with care. N raised to the power of 1 equals n. This completes the review of the arithmetic course. Thank you for watching the entire series. If you'd like to download the full printable slides, the exercises, and the final cheat sheet, you can find everything on Gumroad. Link in the description and in a pinned comment. Thank you again for following the course. See you in the next series.